Good morning, everybody. My name is Anita Winter. I'm a probabilist from the neighboring University of Duisburg-Essen. It's my great honor to introduce Rongfeng from National University of Singapore. Rongfeng has a very strong publishing record and done some groundbreaking work on scaling limits of interacting particle systems and disordered systems, and is best known for his work on the Brownian web and the Brownian net, as well as on the two-dimensional stochastic heat equation and the KPC equation. He has been recognized among faculty at National University of Singapore for the Outstanding Scientific Award in 2023. Rongfeng Sun has a long tradition of public service to the community. He was the associate editor of the IMS-supported journal, Electronic Journal of Probability, Electronic Communications and Probability, and the Journal of Mathematical Physics, Analysis and Geometry. He is currently a member of the Committee for the Conference on Stochastic Processes and has served on the Scientific Committee of the SPA in 2019. It's my great pleasure now to announce that the Bernoulli Society and the IMS has chosen him to be the awardee of this year's Levy Lecture. And as usually, this comes for certificates.
Okay, I hope everybody can hear me clearly. So yeah, thanks Anita for the introduction, and thanks for the invitation to give the Levy lecture. So it's a great honor and a pleasure. Okay, so I'll talk about something that lies at the interface of so-called singular stochastic partial differential equations and disordered systems. So I'll explain this in more detail later. So almost everything I'll talk about is joint work with my collaborators, Francesco Carrena, so that's the one on the left, Nico Zigras. So when you see CSZ, CSZ is just the first letter of our names. And so I'll refer to CSZ quite often in the later slides. Okay, so we probably all know about the heat equation. So you have a function u in space and time, which models the temperature. So you use it to model how the heat diffuses. It is also called the diffusion equation when u represents the density of a material that is diffusing. So this is a deterministic partial differential equation, and we are interested in the stochastic versions of this, where we perturb the heat equation by a noise term. So the noise term here is given in the form of constant beta times the solution itself times a random potential psi, which in this case will be a space-time white noise. So the significance of this multiplicative term is basically it causes the solution to grow exponentially or decrease exponentially depending on whether the potential psi is positive or negative. So in this case, the random potential psi here actually is not a function. So you may be familiar with what is white noise. So white noise is basically a random generalized function. So this means that you can only make sense of it by integrating it against the test functions. And for white noise, when you integrate against the test function, then you get a Gaussian random variable. And for the white noise at different parts of space-time regions, they will generate independent noise. So the derivative of a one-dimensional Brownian motion is the simplest version of basically one-dimensional white noise. So basically, it's a continuum analog of ID random variables in space and time. And it is not a function. So the fact that it is not a function creates problems for this stochastic partial differential equation, because when the dimension is high enough, then it turns out that the solution U itself would not be a function either. It will be a generalized function or distribution as well. Then in the equation, you have the product of two generalized functions, U times psi. And mathematically, there is no canonical way of making sense of this. So that is why this stochastic partial differential equation is called a singular SPD. And that's a generic defining feature of singular SPDs, namely that the equation always contains terms which involve products of generalized functions or some nonlinear function of a generalized function. So that's why these are called singular SPDs. So I will be mainly interested in the stochastic heat equation in the dimension 2. And dimension 2 will be special, as I'll explain. So the stochastic heat equation is also interesting because if I take the logarithm of the solution of the stochastic heat equation, although formally at this point, then this is called the Kohoff transformation. So by the Kohoff transformation, you obtain a new function h, which formally solves the so-called Carta-Parisi-Zhang equation, the KPZ equation, which has been studied extensively in the probability literature in the last 20 years. So if you look at the equation itself, then you still have a heat equation part. However, now you also have a nonlinear term, which is a gradient, the spatial gradient of the solution squared, and then the noise becomes additive instead of multiplicative. Right? We don't have the noise multiplied by the solution itself, unlike the stochastic heat equation. So this is called the additive noise, when the noise is not being multiplied by the solution. So the KPZ equation is interesting because the solution itself represents the height of a randomly growing interface. So in dimension 1, this leads to the so-called KPZ universality class. So in particular, if you look at the solution at the position x at time t, then as time goes to infinity, the stochastic fluctuation of the height function converges to the so-called Tracy-Widom distribution, which appeared originally in random matrix theory. So here is two pictures illustrating. So on the left, that's a picture of the burning front of a forest fire. On the right, it's the colony of bacteria growing. So if you look at locally, the surface is a bit rough, right? So it's a one-dimensional surface, and so it's a bit rough. So if you zoom in at the large time scale and you look at the fluctuation of the surface, that is essentially governed by this one-dimensional KPZ equation. So that's also the interest of stochastic heat equation in the sense that it is connected to this physically relevant surface growth model. And in this case, it is also a singular SPD because gradient of h will be a generalized function. So again, you have the square of a generalized function, and that is mathematically undefined. So that was the work of Martin Herrer, who showed that KPZ, among other singular stochastic PDEs, it is possible to make sense of these square of generalized functions and give a rigorous solution theory for this kind of, for the one-dimensional KPZ equation and other singular SPDs. So there's been a lot of progress in the solution theory for singular SPDs, starting with the work of Martin Herrer. There are also other theories, such as pyro-controlled calculus by Gubinelli, Imkeller, and Bekovsky. And there's also the renormalization group approach of Gubianden. There's been a lot of further progress in recent years, so I don't have space to list all of them. But this is one of the most active areas of research in probability theory in the last 20 years. However, a limitation of all these theories is that the theories I've listed, they only apply to a class of singular SPDs which are called the subcritical. So for the stochastic heat equation and the KPZ equation, subcritical means dimension has to be strictly less than 2. So it just means basically dimension 1. So for dimension 2, that will be the critical case for which the solution theory cannot be applied. And dimension larger than 2, this will be the supercritical case, and the solution cannot be applied either. So there is a close connection between singular SPDs and quantum field theory. Both have to do with trying to renormalize away the infinities that appear. And so subcriticality for single SPD basically corresponds to something that is called the super renormalizable quantum field series, while criticality for single SPD corresponds to so-called renormalizable quantum field series. Okay, so let me try to explain here why dimension 2 is special, is critical for the stochastic heat equation and the KPZ equation. The way to see that is to use ideas from renormalization group, namely that you try to zoom out on larger and larger scales, and then you see that what happens to the system. Does it converge to, what does it converge to? What about the strength of noise? Does the strength of noise blows up? Or what about the strength of nonlinearity? So you try to look at how the model evolves as you zoom out. So here, we try to zoom out by respecting the diffusive scaling, because the heat equation satisfies a diffusive scaling relation. So therefore, we take the original solution, and we define new solution U tilde by scaling space and time, so that 1 unit of time for the new solution corresponds to epsilon to the power of -2 units of time in the original solution. So we are looking at large scales, and epsilon is going to 0. And the 1 unit of space for the new solution corresponds to epsilon to the power of -1 units of space in the original solution. And then you can formally write down what is the partial differential equation that is satisfied by this new function. And you see that the Laplacian, the heat equation part, is preserved. And what changes is the noise term. So what you get is a new space-time-wide noise that you obtain by scaling. But now the prefactor in front of the noise picks up a power of epsilon. So it's epsilon to the power of d minus 2 over 2. In particular, if dimension is strictly less than 2, then we see that as you keep on zooming out by sending epsilon to 0, the prefactor of the noise will diverge. So this means that on larger and larger space-time scales, the strength of noise is actually diverging. While in dimension 2, the strength of the noise does not change as you zoom out. In dimension 3 and higher, you find that the strength of noise will vanish. So it becomes more and more like the heat equation on large scales in dimension strictly larger than 2. So that explains that why dimension 2 is critical, because it is exactly the borderline between when the noise perturbation of the heat equation is relevant on large space-time scales or irrelevant on large space-time scales. Relevant means that as you keep on zooming out, the effect of the perturbation will vanish. Irrelevant means that effect of the perturbation will vanish on large scales. So it's an irrelevant perturbation. And relevant means it's a relevant perturbation in the sense that on large space-time scales, the effect of the noise will diverge. And the critical is basically the marginal case. Dimension 2 is the marginal case. So the main result I want to explain is our progress in trying to make sense of the solution for the stochastic heat equation and to a lesser extent the KPZ equation in the critical dimension 2. Because current solution series of regularity structures, etc., cannot answer this question. So for the stochastic heat equation, we have a much more complete picture, and this is what leads to what the title of the talk is about, which is the critical 2D stochastic heat flow. So critical 2D stochastic heat flow is what we call the solution we defined for the two-dimensional stochastic heat equation. Okay, so now let me try to explain briefly that how do people go about in trying to define the solution of these single SPDs. So remember that single SPD is singular because the white noise is very rough. Rough because local on small scales, it is not a function, and so the roughness is a problem on small scales. And the same with the solution U. So therefore, one way to remedy this is to try to first remove the roughness on small scales by performing some sort of truncation. So this could be some sort of smooth, so you can do it by smoothing. And in physics language, this is called the ultraviolet cutoff, because ultraviolet light has high frequency. High frequency translates to small wavelengths. And so when you do this cutoff, you are basically cutting off what happens on small scales. You are cutting away this roughness on small scales. And there are several ways of doing this ultraviolet cutoff of small scales. So the standard way is to modify the white noise spatially with a smooth function on the spatial scale of epsilon. So you take a density function, which is compactly supported, and then you rescale it so that the support now is on the ball of radius epsilon. But it's approximate delta function, so the integral is still equal to 1. And then you convolve the space-time white noise spatially with this modifier. So this will remove the roughness on scale, a spatial scale less than equal to epsilon. So that is one way of doing the smoothing, which introduces a spatial scale epsilon for the smoothing. Alternatively, you can simply discretize the space. If I discretize space by introducing a lattice spacing of epsilon, then of course there is also no more spatial scale that is smaller than epsilon. And yet a third way is to look at the Fourier transform. And you can cut away all the Fourier components with a frequency that is larger than 1 over epsilon. Because large frequency means a small wavelength, small spatial scale. So therefore, if you remove all the contributions from high frequency modes, then you are essentially also removing the variation on the small spatial scales. So these are different ways. And we expect that doesn't matter which way of smoothing you do, when you try to remove the smoothing, remove the ultraviolet cutoff, then you should get the same universal limit. So that is the general philosophy. Now, coming back to singular SPDs, what the people want to do is that by first performing a smoothing, you obtain a stochastic partial differential equation that is well-defined in the classical sense. And then we want to send epsilon to 0 and remove the smoothing and see that what the limit do you get. Of course, if you just do it naively, you'll get infinity. Just like in quantum field theory, if you remove the ultraviolet cutoff, many theories will have blow-ups. And so therefore, you need to do some renormalization. And what we mean by renormalization includes centering of the solution by constant that varies with epsilon, rescaling of the solution by another constant factor that depends on epsilon, or also possibly tuning of the parameters of the equation. That is also allowed. And if you, after this centering, scaling, and tuning, you can get the non-trivial limit, then that limit is normally defined to be the solution of this singular SPD. So this is something that we'll do as well. So it's this centering and normalization which requires the serial regularity structures for these subcritical singular SPDs. But as I said, for the critical case, this does not work. So let me come back to the first scheme of regularizing through modification. So if I modify the noise in space, then you get a stochastic partial differential equation that has a classical solution. In particular, the solution admits a Feynman-Katz formula. Just like the heat equation with the potential admits a Feynman-Katz formula, the stochastic version also has a Feynman-Katz formula. So if you want to know the solution at time t at position x, then you have to run a Brownian motion starting at position x at time t, and then you run it backwards in time, and you see that what is the potential that you see along the trajectory. And then you integrate the potential along the trajectory, you normalize it, and that defines the solution. So that's a Feynman-Katz representation. And in dimension 1, Bernoulli-Congrini showed that for the stochastic heat equation, if you modify it, the noise, then actually there is no need to do centering and scaling. The solution, the modified solution simply converges to limit, and the limit is a function as well. So that is the solution of the one-dimensional stochastic heat equation. Taking logarithm of this gives the Kohoff solution of the one-dimensional KBZ equation. Alternatively, you can discretize the space. And so we'll actually discretize space and time simultaneously so that you get a discrete lattice model. And so you'll get a similar Feynman-Katz representation, but in that Feynman-Katz representation, you get a random walk instead of Brownian motion. Instead of getting white noise in space and time, you get the discrete analog, which is basically a family of ID random variables indexed by the lattice points in space and time. And that turns out to be what we call as the partition function of a different model that is called the directed polymorph model. So that is a disordered system, and that brings us to the title which says the singular SPD meets a disordered system. So it's this connection to the directed polymer that brings us to the disorder system I referred to in the title. So now let me explain what is the directed polymer. So basically, I'm going to follow the second approach of regularization. I'm going to discretize space and time to make sense of the two-dimensional stochastic heat equation instead of modifying the noise. And if I discretize space and time, then I get the directed polymer model, which is defined in the following way. So the basic ingredients are the simple symmetric random walk. So here I draw the random walk as going downward in time, just to be consistent with the Feynman-Katz representation of the solution of the stochastic heat equation. Instead of getting Brownian motion, you get a random walk going backwards in time. And there is a time horizon, which is capital N. So there is a fixed time horizon, just like the stochastic heat equation. There is a time that you are interested in examining the solution. And then you get ID random variables indexed by the lattice points. So for the directed polymer model, we think of it as the random environment or disorder. Now, the directed polymer model is defined as a random probability measure on the random walk trajectories. So if I fix the realization of the random environment, then I fix the time horizon capital N, so that the random walk has time duration N. And I also fix a parameter beta, that is the strength of the disorder, or also called the inverse temperature. Then I can define a so-called Gibbs change of measure of the random walk in the following way. So the reference measure is the random walk measure from time 0 to time n. But then I'm going to change the weight of the random walk trajectory by an exponential factor, where in the exponent, you get a beta, which is the strength of the interaction, multiplied by the disorder variables that you see along the random walk trajectory. So that's exactly similar to what is we saw in the equation 3 for the Feynman-Katz formula for the stochastic heat equation. You integrate the random potential or random environment that you see along the trajectory, and that exponential weight changes the law of the random walk. So in connection with the stochastic heat equation, we want to consider different starting points in space and time. Sorry, I forgot to mention that the denominator here is a normalizing constant, which makes it a probability measure. So therefore, it is simply the expectation of the exponential weight with respect to the random walk. And that is called the partition function for the polymer starting from point 0, 0. So that is analogous to the solution of the modified stochastic heat equation at the 1 point t and x. So in connection with the stochastic heat equation, we also want to consider polymer with different starting points in space and time, even though the terminal time is still the same. So that's what we define partition function at starting from point x at time n, and the definition is similar. So if I consider this whole family of partition functions with different starting points in space and time, then that is exactly the discrete analog of the solution of the modified stochastic heat equation through the Feynman-Katz formula. So in particular, if I rescale space and time diffusively to make the lattice spacing, or equivalently make the lattice spacing smaller and smaller, then this is in perfect analogy with the modified stochastic heat equation. In particular, if I rescale space and time diffusively, then it introduces a lattice spacing, which is 1 over square root of n, which corresponds to the spatial scale epsilon for the modification. Okay, so for the stochastic heat equation's point of view, then the question we want to understand is that this family of partition functions, which are basically solutions of discretized stochastic heat equation, do they have non-trivial limit as n goes to infinity? Remember that 1 over square root of n now plays the role of lattice spacing. So if the answer is yes, then we can define the limit to be the solution of the two-dimensional stochastic heat equation. So to answer this question, we need to have a better understanding of the directed polymer model that is associated with these partition functions. So therefore, let me try to explain heuristically what is the phase transition underlying the directed polymer model. So here is, again, the formula for the Gibbs measure of the polymer. with time duration n. The first observation is that if I start with beta equal to 0, then the random environment or disorder has no effect. So this part is just a constant to make sure that the partition function has expectation 1. So you can ignore this. So if I start with beta equal to 0, then we see that you just get a random walk measure. So in particular, random walk is diffusive. It satisfies invariance principle. The displacement at time n is of order square root of n. However, if I make beta larger and larger, then the measure is going to put more and more weight on trajectories which visits regions of space and time with large values of omega. So the effect of the Gibbs weight is to put more weight on trajectories that visits favorable regions of the environment with large values of disorder, large values of omega. And in the extreme case, when you set beta equal to infinity, then the Gibbs measure on the random walk trajectories will concentrate on the single trajectory where the summation of these weights or disorder is the largest among all trajectories. There are only finite set of trajectories because we assume the random walk is simple. And so if beta tends to infinity, then the Gibbs measure will concentrate on the single trajectory. And that is basically what is known as the last passage percolation model. If you think of omega as a passage time for fluid to flow through that edge, then you are trying to maximize the passage time among all possible routes you can take. In dimension 1, last passage percolation model belongs to the KBZ universality class. So the fluctuation of the last passage time has trace within the distributions. Even though this has only been proved for special integrable models, we believe that this is a universal result. And if I look at the location of this optimal trajectory, then it has been proved for the integrable models that the transversal fluctuation of the random walk is n to the power of 2/3 instead of square root of n. So that is so-called a super diffusive fluctuation. And again, this is believed to be true in general, but rigorous results are restricted to integrable models. So this indicates that as you vary beta, we are going to see a change of behavior. And so that's where the phase transition comes in. So what we can prove is that there is, so what is known in the literature is that there's a critical value of the disorder strength or inverse temperature, called the beta C here, such that if you are below the critical point, then the polymer behaves like a random walk with a diffusive fluctuation. And furthermore, this is seen in the fact that the partition function converges as the time horizon tends to infinity, the partition function converges to a strictly positive limit. On the other hand, if beta is above the critical point, then the partition function converges almost surely to 0, and the polymer itself is believed to be super diffusive. So this is still largely conjectural. So we have a different way of characterizing the phase transition in terms of so-called localization or delocalization, which is to say that if I sample two polymers independently from the same random environment, how much do they overlap? And in the subcritical phase, because they are like independent random walks, so they overlap very little. But in the supercritical case, then they are going to visit essentially the same region of space and time where the environment is favorable, and this leads to localization of the trajectories. So that is the phase transition for the directed polymer model, and which is seen also in the convergence of the partition function to something that is 0 or non-zero. And compared with the directed polymer model, where you can also think of the noise as a disorder perturbation of the heat equation, here the directed polymer model, you can think of it as a disorder perturbation of the underlying random walk. And then the natural question is that, is this perturbation going to lead to drastic change of behavior when you look at the large space-time scales? So we say that this perturbation by the random environmental disorder is a relevant perturbation if the presence of any disorder, no matter how weak it is, will drastically change the qualitative behavior on large space-time scales. If that is true, then we say that this perturbation is a relevant disorder perturbation. So we call it disorder relevance. So that was, for example, if you change the fluctuation exponent from diffusive fluctuation to super diffusive fluctuation, that will qualify as a a relevant perturbation. That will qualify as qualitative change of large-scale behavior. So normally, there are other critical exponents that tells you that whether the model has changed its universality class or not. So that's a disorder relevance. Arbitrarily small perturbation by disorder changes the universality class or changes large-scale qualitative behavior. On the other hand, if small perturbation does not change the large-scale behavior, then we say that this is an irrelevant perturbation. So that is very similar to the stochastic equation we saw, where we saw that in dimension less than 2, the disorder perturbation is a relevant perturbation for large scales, and the disorder perturbation is irrelevant for dimension larger than 2. So I'm not citing a lot of literature, so let me just refer to some floor lecture notes, which is now a book by Francis Gomez on the directed polymer model, if you are interested in more about the directed polymer model. So what we know is that for directed polymer model, the critical disorder strength or inverse temperature actually is equal to 0 in dimension 1 and 2. Now what this means is that in dimension 1 and 2, as soon as beta is larger than 0, or in other words, there is disorder present, then you are expected to have super diffusive behavior. So therefore, disorder perturbation is a relevant perturbation because arbitrary small disorder will change the qualitative behavior of the model. In dimension 3 and higher, on the other hand, it is known that the critical point is strictly larger than 0. So therefore, if I perturb the model by disorder that is weak enough so that you are below the critical point, then the large-scale behavior is the same as a random walk. So therefore, this is the irrelevant perturbation. While dimension 2 is the critical dimension, just like for the stochastic heat equation. Even though it is a relevant perturbation, it is only marginally relevant. So that is called the marginal relevance. So therefore, by now we see that there is a correspondence between the notion of subcriticality for single SPDs to the notion of disorder relevance for disorder systems, which corresponds to super-renormalizability in quantum field theory. And similarly, supercriticality for single SPDs basically corresponds to the notion of disorder irrelevance, while criticality for single SPD corresponds to the notion of marginal relevance or irrelevance. So we are basically connecting the terminology in these two different areas of research. One is single SPDs, the other is disorder systems. In disorder systems, in general, there doesn't need to be a time dimension. While in SPDs, there is always a time direction. But in disorder systems, you don't need to have a time direction in general. But still, you have this correspondence. So again, connecting with the scaling limits kind of questions were interesting for SPDs, we want to understand what are the possible continuum limits, whether you can get continuum limits that are non-trivial, that have non-trivial dependence on disorder. This can only be done for models which are disorder relevant. The disorder perturbation is relevant. Because if the disorder perturbation is relevant, it means that if I look at things on large space-time scales, or equivalently, I make the lattice spacing smaller and smaller, then what we see is that the model is going to change drastically. Another way of saying it is that the effective strength of disorder is divergent as you make the lattice spacing smaller and smaller. So therefore, one way to compensate this is to change the strength of disorder as the lattice spacing goes to 0. You tune down the strength of disorder down to 0 as well at a suitable rate, exactly to compensate the fact that, in some sense, the effective strength of disorder is divergent. So therefore, for disorder-relevant models, it is hopeful that we can tune the strength of disorder to get the non-trivial limits. And in particular, for models which are defined through Gibbs measures with partition functions, then the first sign that such a non-trivial disorder limit should arise will appear through the limit of the partition functions themselves. And that connects again to the partition functions of the direct polymer model and the interpretation through SPDs. Okay, so here's some existing results on scaling limits of disorder-relevant models. So the first result in this direction is the work of Alberts, Canning-Quastel for the directed polymer in dimension 1, which is still disorder relevant. And they show that if the strength of noise as a function of the length of the polymer decays to 0 like a constant beta hat over n to the power 1/4, then the family of diffusively rescaled partition functions converges to the solution of the one-dimensional stochastic heat equation. So that is the analog of the result of Bernoulli-Concrini with a modified noise instead of discretized space and time. But the Albers-Koenig-Pastel also used the limiting partition functions to define a continuum analog of the directed polymer model. And in the subsequent work with Francesco Nichols, we realized that this scheme actually should work for disorder-relevant models in general. And so we formulated a general criterion that can be applied to the partition functions of general disorder-relevant models, which includes in particular the random field perturbation of the critical 2D Ising model. And we use it subsequently with Adam Bowditch. We constructed a continuum random field Ising model as well, which is defined using Fourier transform of the spin field. So it is still open question whether you can define the continuum random field Ising model through interfaces, which are some sort of disorder versions of SLE. So that is still open. But that theory is also only for disorder-relevant models, not for the critical dimension. And for the critical dimension 2, for the directed polymer, will require very different techniques. And so this is what I want to come to now. Okay, so our first observation in our research on the two-dimensional directed polymer model and the stochastic heat equation is the fact that even though, as I showed you before, in dimension 2, the critical parameter, the critical point is still equal to 0, the critical inverse temperature is still equal to 0. However, there is still phase transition on the so-called intermediate disorder scale, where allow the inverse temperature to vary with the time horizon n. So the correct way to scalate the strength of the disorder is to define it to be a parameter beta hat divided by the square root of the overlap of two random walks. So you take two independent random walks in dimension 2 on the ladders, and you compute the expected number of times they collide with each other up to time n. That is what we call overlap, and defined by Rn here. So in dimension 2, this diverges like a constant times log n. So therefore, we are essentially rescaling the strength of disorder by square root of log n. Then it turns out that there is a phase transition on this intermediate disorder scale, where the critical point of a beta hat, the number sitting in the numerator, the parameter sitting in the numerator, the critical value is exactly equal to 1. So when you are below the critical point, we can show that the partition function, starting from a single point, converges to a log normal random variable. While if you are at or above the critical point, the partition function converges to 0. And that is exactly in analogy with what we saw for the directed polymer model itself. In the subcritical regime, the partition function converges to a positive limit. In the supercritical regime, the partition function converges to the 0 limit. So it's exactly this kind of phase transition, which translates to localization and delocalization. So this is our first observation, first result. And our second result is to show that if you are below the critical point, then if we look at the family of rescaled partition functions as a random field, right? Random field in the sense that you hit it against the test functions, try to make sense of that. Then the random field, if I center it by the mean is always equal to 1. And then I renormalize it by blowing it up by a factor of square root of log n. Remember, beta n is basically 1 over square root of log n. So I blow up the centered field. Then at the random field, it converges in distribution to a non-trivial limiting random field. And the limiting random field is a Gaussian field. It is a generalized Gaussian field. And it solves the so-called additive stochastic heat equation, where the noise is being multiplied by this prefactor here. Okay, and you see that it's also a phase transition in the sense that this will diverge as beta hat goes to 1. So that is a subcritical regime, the way we show that actually there is a Gaussian limit if you are below the critical point. And now lastly, as title suggested, the critical 2D stochastic heat flow arises in the critical regime where beta hat is equal to 1. And in fact, there is a critical window around this critical point if you add a second order term. And so this is our main result, which show that in this critical window, if I look at the family of rescaled partition functions, without any centering and rescaling, just treat it as a random measure, then there is already a non-trivial limit. And the limit is dependent on the parameter theta I choose in the critical window. So that is what we call the critical 2D stochastic heat flow. Okay, so here are some simulations by Matteo Mucciconi and Nico Zigras. And on the left-hand side, and there is some natural landscape, so that's a meteora. So I borrowed these slides from Nico Sanfrancesco's talk. So you can see that Nico's pick meteora. So this is another simulation compared with Bryce Canyon. And this is another simulation compared with Dubai. So you see a lot of peaks. So the peaks, because the measure is basically singular with respect to the Lebesgue measure. So that's why you see the peaks. So this is the logarithm of the partition function. So essentially, it's a discrete version of KPZ. And you can compare with the Alps. OK, so I'm running out of time, so let me try to wrap up soon. So just some comments. So first of all, the critical 2D stochastic heat flow gives a meaning to the solution of the two-dimensional stochastic heat equation, which is interesting because it goes beyond the existing solution series for the subcritical single SPDs. And it is also interesting because it is one of the rare examples where you get a non-trivial limit for a model that is in the critical dimension and at the critical point. For the easy model, dimension 4 is a critical dimension, but at the critical point, Hugo Dominic-Goupin and Eisenman have shown that the limit is Gaussian. So here the limit is non-Gaussian. So there are some early results before our work which study the moments, but the moments diverge too quickly to characterize the limiting random measure. So that's why I have to prove it by hand. And for the moment, we still do not have a characterization, an axiomatic characterization of the critical 2D stochastic heat flow. So then how do you prove that there is convergence to unique limit without axiomatic characterization of the limit? Well, the way we do that is to show that the laws of this random field, they form a Cauchy sequence. And so therefore, they converge to unique limit. And the way to do that is by coarse graining. I introduce some sort of coarse grained model on the mesoscopic scale. And all the models with different lattice spacing can be compared to the same coarse grained model and then show that they are close to each other. So another model that has been shown to converge to a unique limit without being able to characterize the limit is the limit of the three-dimensional loop erase random walk by guided Cosma, where it is also shown to converge to a unique limit, but the limit still lacks a characterization up to now. And so some properties of the critical 2D stochastic heat flow include scaling relations. If I zoom out, then the effect is to increase the strength of disorder. And almost surely, the stochastic heat flow as a random measure is singular with respect to the Lebesgue measure, but it has no atoms. And it is barely not a function because it is alpha holder for any alpha less than 0. So it barely loses the regularity to be a function. And long-time behavior, it converges to the 0 measure locally. If you start with the Lebesgue measure, you run it up to time t and let it to go to infinity. Locally, it will converge to 0 measure. And if I send the disorder parameter theta for the stochastic heat flow to -infinity, then you get a Gaussian fluctuation. So therefore, the critical 2D stochastic heat flow interpolates between a Gaussian Gaussian regime on the one side, where theta goes to -infinity, and another side, which is theta going to +infinity, that we still don't quite understand. And the last result I want to mention is that in the earlier work, we showed that as a random measure, the critical 2D stochastic heat flow cannot be a Gaussian multiplicative chaos in the sense that it cannot be realized at the exponential of a generalized Gaussian field. So this is sort of suggesting that if we can take the log to get a 2D KPZ, critical 2D KPZ, then the critical 2D KPZ probably is not Gaussian. But of course, we cannot take the log of a random measure, which is not a function. So there's more simulation by Francesco. So you see a lot of spikes because of singularity with respect to the Lebesgue measure. And lastly, let me just mention some open questions. So one is characterization of the critical 2D stochastic heat flow. This could be martingale problem characterization or could be some axiomatic characterization. Study more properties of a critical 2D stochastic heat flow, especially as theta goes to infinity. What can you say about the limit theta goes to infinity? Defining continuing directed polymer similar to what was done in dimension 1. Fluctuation of the logarithm of the partition function, because that is interesting in the sense that in dimension 1, that's what gives a Tracy-Witten fluctuation. So do we have something like a 2D analog of the Tracy-Witten? That is wide open. And of course, we want to define the critical 2D KPZ, which we are still not able to define at the moment. We only define critical 2D stochastic heat equation. And what about other marginally relevant disordered systems that do not have a time dimension? Is it possible to obtain non-trivial scaling limits as well? And so a lot of what I talked about will be included with more references in our forthcoming lecture notes with Francesco and Nikos. So we should be able to post it before the end of the year. So there are some references, and I think that's all. Yeah, thank you for listening.
Many thanks, Hongfeng, for this beautiful talk. I think we do have time for a few questions. Frank.
So, Hongfeng, is there something, let's say, that you could say in the neighborhood of the model that you've looked at now to which you could extend this? So, because people also talk about this KPZ class and all sorts of models that are in this, can you include them, or are they included?
You mean the sort of how general is our approach?
Yeah.
Unfortunately, our approach is restricted to the stochastic heat equation because the equation is linear. So we can use like a chaos expansion and things like that. So if you switch to 2D KPZ, then because of nonlinearity, we are not able at the moment to define the critical 2D KPZ. For subcritical, we have already proved that you get the same Gaussian limit as the stochastic heat equation. So that's the same.
Okay, thank you.
Could you pass there?
Thank you. Is that the case that the partition function for the 2D directed polymer happens to be also the solution to a discretized stochastic heat equation?
Sorry, I didn't understand the question.
Oh, is that the case the partition function itself can be considered as a solution to some equation? Like it's like because you want the equations to approximate your end equation.
Okay, so the partition function, they are basically a solution of the space-time discretized stochastic heat equation. But in the continuum limit, we don't have an equation in the sense that we cannot say that the critical 2D stochastic heat flow is a fixed point of some transformation. Like in regularity structures, they always say that the solution is a fixed point of some transformation. That we do not have in the critical 2D case.
Thanks.
Thank you for your nice talk. My first question, in your case, the noise is a beta multiplied the U and the Kc, so it's a linear multiplicated noise. When this U before the Kc is a general function sigma U, if it has strong nonlinearity, for example, polynomial, could be this solution blew up in finite time, in some stopping time?
Yeah, so if you replace the noise term by some nonlinear function of solution multiplied by xi, then there is believed to be, so as long as the sigma, the nonlinear functional is Lipschitz, or at least locally Lipschitz, then there are some results by various people like Rentau and Dunlop and Gu and Coleman, where they have looked at this, and but it's not clear that what is the critical point in this nonlinear case. So all the results are basically within the equivalent of the subcritical regime, where you can show that you get point-wise, also random field-wise and point-wise, you can identify the scalar limits of the solution of this nonlinear stochastic heat equation dimension 2.
And my second question, and you present example, and the critical point for the beta C is 1. And if the dimension, for example, greater than equal to 2, could we characterize the critical point, the beta C, numerically or analytically?
Okay, so in dimension 3 and higher, there is also a critical beta hat, and so that is basically the critical point of the directed polymer model. And for the directed polymer model, we do not have an explicit calculation of the critical point. And so there have been similar results in looking at the stochastic heat equation dimension 3 and higher. And what they can do is that below the L2 critical point, the point where the second moment of the partition function becomes infinite, then you can get results which are similar to what we see in dimension 2. And the same for KPZ. But the value of the critical point is not known and is probably not going to be helpful in understanding the phenomena itself. And so there is the problem is mostly open beyond the L2 critical points.
Thank you.
Possibly one more last question. Doesn't seem to be the case, so let's thank Rongfeng again. And let me also mention that Rongfeng will be here until the end of the conference, so you can, of course, also ask him personally. And as many of you already know, the Ruhr University is the only university which produces their own perfume. They do research on this, and as a local organizing committee, we would like to give you, Rongfeng, as a present, this perfume of the brand Knowledge.
Thank you.
Okay, so I'm Alice Guillonnet. I'm a CNRS researcher in École Normale in Lyon, and I have the pleasure to introduce Nina Holden from Current Institute in NYU. So Nina Holden is a Norwegian, and she was the first woman to win the Abel competition, the Norwegian Olympiads. She came to MIT in 2013, I think, and I had the pleasure to meet Nina then, and I think she had to endure a couple of my lectures. And then she defended her PhD thesis under the supervision of Scott Sheffield in 2018. She obtained stellar results in random geometry, Liouville quantum gravity, and random triangulation. And for her work, she was awarded the Mariam Mirzakhani New Frontier Prize in 2021 and the EMS Prize in 2024. So I have the pleasure to present her the certificate for her Schramm lecture. So I think we have to go there.
Thank you.
Without further ado.
Yeah, Thank you very much for the introduction. It is a big honor for me to give the Schramm lecture at this Congress. Odo Schramm is a person who I unfortunately never had a chance to meet myself, but he is still a person who had an enormous impact on me and my work. Schramm is probably most well known for his discovery of the Schramm-Leuven revolution, or SLE, but he also did very influential work on other topics, including discrete conformal geometry, random planar maps, random walk, and percolation. All of these topics will play an important role in this talk. The Schramm-Leuven revolution, or SLE, will actually not be mentioned much, but I still want to mention that the SLE is playing a very important role in the proofs of the results I will be presenting. In fact, none of the theorems I am presenting in this talk would have existed if it wasn't for Schramm's discovery of the SLE. The primary object that we will be studying in this talk is random planar maps, and what you see here on the slide is one of Odo Schramm's most influential papers on random planar maps. It's called Uniform Infinite Planar Triangulations, and it was co-authored with Omer Angel, who was Schramm's PhD student at the time. So the authors start the paper by asking what is a generic planar geometry. They say that there are many different planar geometries, and that the most commonly considered one is the Euclidean plane, but they ask whether this is generic. Further down, they say that the approach they are using is to consider a probability measure on planar geometries, and a probability measure which in some sense can be viewed as a uniform measure. More concretely, they consider discrete geometries realized in the form of planar triangulations. So what is a triangulation, or more generally, what is a planar map? A planar map is a graph drawn on a sphere without edge crossings, which is viewed modulo continuous deformations. For example, in the planar maps in the left and middle parts of the figure, they are considered to be the same planar map, since we can get from one to the other by doing a continuous deformation. The planar maps in the middle and right parts of the figure, on the other hand, are not considered to be the same. Viewed as graphs, these two maps are the same, but viewed as maps, they are different, because the planar embedding is different. So you see that in order to get this planar map from this planar map, then this edge has to be moved here. Given a natural number n, there are finitely many planar maps that have exactly n edges. And we get a natural uniform or generic planar geometry by picking a planar map uniformly at random from such a finite collection of planar maps. So going back to the paper of Angel and Schramm, they are considering infinite planar maps, meaning planar maps with infinitely many vertices. In most of this talk, on the other hand, we will be considering finite planar maps, so planar maps with a finite number of vertices and edges. So in this figure, you can see some large random planar map, which has been embedded into R3. If you have some large random planar map, then it's typically not possible to embed it isometrically in R3. So it's typically not possible to draw it in R3 in such a way that all the edges have the exact same length. So in making this drawing, one has attempted to make an embedding which is in some sense as close to isometric as possible. So the various edges have a length which is as close as possible. In this figure, you can see a photograph of a 3D printed random planar map, which has been made by Maurice Ang. I actually brought this 3D printed random planar map with me to the conference, and I have it here in my hand. So in case anyone is interested in having a look, you can come and see me after the talk. So here is part of the paper by Angel and Schramm on infinite planar triangulations. Planar maps, they are studied in many different branches, so both math and physics, and Angel and Schramm discuss some of these applications. The study of planar maps in the math literature goes back to the 60s, where Tutt, Mullin, and others were proving enumeration or counting formulas for planar maps. They're also used in physics, for example, in the study of 2D quantum gravity. Here, random planar maps are used as models for random surfaces. And these are just two out of many contexts where planar maps are appearing. So if you look at this text, you see that several places the authors are discussing the asymptotic properties of planar maps when the size is going to infinity. For example, they are saying that the diameter of a planar map equipped with a graph distance, it is scaling like n to the power a quarter when the size n of the planar map is going to infinity. Further down, they're saying that the random planar maps should have a continuous scaling limit. So when the size of the planar map is going to infinity, then in some sense it is converging in law to some continuum limiting object. This paper of Angel and Schramm was written more than 20 years ago, and significant progress has been made since that time. So in particular, we now have a quite good understanding of the asymptotic properties of uniformly sampled planar maps. And in particular, we have established a number of scaling limit results. So now I want to give a brief overview of these results. So we suppose that M sub n is a uniformly sampled planar map of size n. A natural question is whether M sub n is converging in some sense when n is n to infinity. And the answer is yes, and the limiting object is what we call a Liouville quantum gravity surface, which I will be introducing on the next two slides. Then the second natural question is what it means that the planar map is converging in law. So when I claim that M sub n is converging in law when the size goes to infinity, what's the precise mathematical meaning of this statement? And there are actually several different ways to formulate convergence results for planar maps. So first, one can talk about convergence in metric topology. So a planar map is a metric space if it is equipped with its graph distance, and one can try to prove convergence of this random metric space when the size of the planar map is going to infinity. This notion of convergence is also, or this topology of convergence is also known as the Gromov-Hausdorff topology. Second of all, one can talk about the mating of trees topology. The idea here is that we are considering some statistical physics model on the planar map, and we're showing that a particular observable of this statistical physics model is converging when the size of the planar map is going to infinity. So these two first notion of convergence, metric topology and mating of trees topology, they have been considered in a number of different works, and for a number of different random planar map models, one has managed to prove that the planar map is converging in these senses as the size is going to infinity. So these results will not be the topic of this talk. So in this talk, we will be focusing on the third notion of convergence, known as convergence in conformal topology. The idea here is that we are viewing the planar map as some random surface with a conformal structure, and we prove a convergence of this random surface. More precisely, I will be presenting two different convergence results in conformal topology. The first result is a result that was obtained in collaboration with Shin Sun a few years ago, and the second result is a work in progress. So strong relationships between planar maps and continuum Liouville quantum gravity was first predicted in the physics literature, and the physicists used this prediction for several purposes. For example, they used these predictions to predict exponents and dimensions associated with statistical physics models at criticality. So the next goal of my talk is to introduce Liouville quantum gravity. So I want to explain what is the precise mathematical object we refer to when we talk about LQG surfaces. In order to do this, I first need to introduce the Gaussian free field. So to do this, I let D be a subset of the complex plane. The Gaussian free field in D can be heuristically defined to be the random function which has been sampled from the measure shown on the slide. Here d phi is the Lebesgue measure on the space of real-valued functions of D, and we take this Lebesgue measure and we reweight it by e to the power minus the integral shown on the slide. The definition of the GFF as given here is not making rigorous sense because, for example, because I haven't specified what I mean when I talk about Lebesgue measure on the space of real-valued functions. However, some variant of this definition can be made rigorous sense of. And the resulting object is actually not a random function. So the Gaussian free field turns out to be too rough and irregular to be well defined as a random function. Instead, the Gaussian free field is well defined as a random distribution or a random generalized function. This means that if z is some fixed point in the domain D, then h of z is almost surely not well defined. However, if f is some smooth test function, then the integral of f against h is well defined, and this will be some random real number. More precisely, one can argue that with probability 1, h is some element in the subbolus space h minus epsilon for any strictly positive epsilon. One can also argue that the Gaussian free field is a Gaussian field and that the covariances are logarithmic. So when the 2 points are approaching each other, then the covariances are blowing up logarithmically. So a heuristic definition of an LQG surface is that it is the random 2D Riemannian manifold where the metric is given by the standard Euclidean metric and locally reweighted by e to the power gamma h, where gamma is some parameter between 0 and 2 and h is a Gaussian free field. This definition is not making a rigorous sense because h is a distribution and not a function, so it's not obvious what e to the power some constant times h means. However, the area measure associated with this surface can be defined in a rigorous way. So this should be the area measure that has density e to the power gamma h relative to Lebesgue area measure. The idea of the construction is to let h sub epsilon be some regularized version of h. So h sub epsilon is a smooth function, which in some sense is approximating h. Then one can use h sub epsilon to define a natural area measure, and then one can show that this area measure is converging upon appropriate renormalization when the regularization parameter epsilon is sent to 0. And the resulting measure is the rigorous definition of what we call the Liouville quantum gravity area measure. Random surfaces, as introduced on this slide, they were first introduced in the physics literature in a very influential paper by Polyakov in the early 80s, which was written in the context of string theory. And in more recent years, these random surfaces have been a very active field of study in probability theory. The study in probability theory was initiated in the 2 works that you can see cited on the slide last. So in the figure, you can see an illustration of the random area measure mu. So the different colors in the figure is representing the density of this random area measure with respect to Lebesgue area measure. The red regions, they correspond to high-density regions, where the Gaussian free field is particularly large, whereas the blue regions correspond to low-density regions, where the Gaussian free field is particularly small. I also want to remark that when the parameter gamma is equal to the square root of 8/3, then the LQG surface is equal to what we call, or equivalent to what we call, a Brownian surface. So this fact will actually not be playing any role in the remainder of the talk, but I want to mention it because many of you may have encountered Brownian surfaces in other contexts, for example, the Brownian map. The precise definition of LQG, as given on this slide, will actually also not be used in the remainder of the talk. So the only thing which we will encounter later in the talk is this random area measure mu. So the only thing you need to remember for later in the talk is that Liouville quantum gravity is giving us some natural way to define a random area measure in some subset of the complex plane. So next, I want to explain what I mean when I talk about convergence in conformal topology of planar maps. So I want to elaborate on the notion of convergence mentioned in the 3rd bullet point on this slide. In order to explain what it means that a planar map is converging in conformal topology, then we first need to define what we call a discrete conformal embedding of the planar map. So this means that we define some function phi on the vertex set of the planar map, and this function phi is taking values taking its values in the sphere S2, or more generally in some subset of the complex plane. So this is illustrated in the figure, where on the left-hand side you see some random planar map, and on the right-hand side you see this random planar map embedded into the sphere via a discrete conformal map. So then the natural question is, what does it mean that phi is discrete conformal? So before answering this question, I want to answer a simpler question. So namely, I assume that phi is some smooth map between 2 domains in a complex plane, and I ask what it means that phi is conformal. And there are actually several equivalent ways to define what a conformal map is. So first, the most commonly considered definition of a conformal map is probably to say that it is a function which is complex differentiable with non-zero derivative everywhere. Equivalently, we can say that it is a function which is real differentiable and satisfies the Cauchy-Riemann equations. One can also get a definition of a conformal map by using Brownian motion. So this is illustrated in the figure. In the left part of the figure, we consider a 2D Brownian motion W, which is started from the point in red, and which is run until it first exits the domain D. We also consider the image of this Brownian motion under some conformal map phi. And conformal invariance just means that the image of a Brownian motion under conformal map, it still has the law of a Brownian motion, at least modular reparameterization of time. And this property can actually be used to characterize conformal maps. So a smooth orientation preserving projection is conformal if and only if a 2D Brownian motion is sent to a 2D Brownian motion. One can also use percolation to define what a conformal map is in a similar fashion as we used 2D Brownian motion in the third bullet point. And finally, one can define what a conformal map is by using approximations via circle packings. So this is just 5 out of many equivalent definitions of a conformal map. So each of these conditions is giving rise to some notion of discrete conformal embedding. So if we're given some planar map, then if you embed it via 2 different discrete conformal embeddings, then these 2 conformal embeddings will typically be different. But it is believed that if you consider some large random planar map, then the 2 different discrete conformal embeddings are approximately the same. Next, I want to explain what kind of discrete conformal embedding we get if we use the third definition of a conformal map, namely the definition using 2D Brownian motion. So first, I need to uniquely fix the conformal map on the previous slide. So on the previous slide, we were considering some conformal map from a domain D to a domain D tilde. And we're now fixing D tilde to be equal to the unit disk. We choose some point A in the bulk, a point B on the boundary, and we require that A is sent to 0 and B is sent to 1. And this is uniquely specifying the conformal map. So our goal now is to define some function phi sub n, which is approximately equal to phi, and which can be viewed as a discrete conformal map. And we will define phi n, so we will let it be a function defined on the graph that you see in the figure. So this is the graph that you see here with vertices colored in purple and gray. So this graph has been obtained by considering Z2, rescaling it by n, and restricting it in some natural way to the domain D. We pick vertices A and B, which are discrete approximations to the points A and B in this figure. So then we want to define the discrete conformal map phi sub n. You can see that the vertices near the boundary, I've colored these vertices in purple, and we refer to these vertices as the boundary vertices. And I will start by explaining how we define phi sub n restricted to the boundary. To do this, I fix some arbitrary vertex v on the boundary, and then I want to define phi sub n of v. And I define phi sub n of v such that the formula in the first indented equation holds. On the left side, we consider some simple random walk on the rescaled version of Z2, which is started from A, and we run this simple random walk until it hits the boundary. And then we consider the probability of the event that this simple random walk is hitting the boundary in this boundary arc colored blue between the points B and V. On the right-hand side, we are considering a 2D Brownian motion Z. It started from 0 and it's run until it exits the unit disk. And we consider the probability of the event that this 2D Brownian motion is exiting the unit disk in the boundary arc between 1 and phi sub n of V. So we require that the formula in the indented equation is holding, and this property is uniquely characterizing the point phi sub n of V. So then we want to define phi sub n in the bulk. So by the bulk, I refer to these vertices that are colored in gray in the figure. The map phi on the previous slide is conformal, and by the Cauchy-Riemann equations, one can see that the real part of phi and the imaginary part of phi are both harmonic functions. Therefore, it's natural to require that phi sub n is what we call discrete harmonic, which means that it satisfies some variant of the mean value property. So more precisely, we require that phi sub n is satisfying the property in the indented equation. So here you can see that phi sub n of v is equal to the average of phi sub n of w, where we take the average over the 4 the 4 vertices that are adjacent to V. So this is illustrated in the figure. So this property can actually also be expressed equivalently via random walk. Suppose that we have embedded a planar map such that it satisfies this mean value property. Then the simple random walk on this graph will be a martingale. And by using optional stopping, we can see that the formula in the parenthesis is holding. So this is the definition of phi sub n. If we're using conformal invariance of Brownian motion, along with the fact that the simple random walk on Z2 converges to the Brownian motion in the scaling limit, then we get that phi sub n is converging to phi when lattice size 1 over n is sent to 0. So the embedding defined on the previous slide is what I refer to as the Tet embedding or harmonic embedding. And this embedding can actually also be defined for planar maps. To be more precise, we need to consider what we call planar maps with disk topology. So a planar map has disk topology if it has a boundary. This boundary is a simple loop which is enclosing the remainder of the planar map, such that the purple curve that you can see in the figure. In the right part of the figure, you can see some large random planar map with a topology of a disk embedded in R3 made by Bettinelli. The red curve that you can see in the figure is forming a loop, and this defines the boundary of the planar map. So here you can see some large random planar map, which has been embedded into the unit disk via the Tet embedding. So this embedding is defined exactly as in the lattice case. So first we pick vertices A and B as in the lattice case, which are sent to the point 0 and 1. Then we embed the boundary vertices via this formula, and then we embed the bulk vertices via this formula. And by using the definition, it's not hard to see that the Tet embedding is well defined, so it always exists and is unique. So it exists and is unique given the points A and B that are sent to 0 and 1. So this Tet embedding, so this is the embedding we get if we use the third definition of a conformal map using a Brownian motion. So I now want to explain what kind of conformal embedding we get if we use the fourth definition of a Brownian motion via percolation. So in the left part of the figure, you can see percolation on the sides of the triangular lattice. So the sides of the triangular lattice have been colored independently at random in blue and yellow. The model is at its critical point if blue and yellow are equally likely. So this is the critical point for having an infinite blue cluster. Percolation was first introduced as a mathematical model approximately 65 years ago, and it was introduced as a mathematical model to explain how fluids move in porous material, for example, a porous stone. The blue sides represent holes, whereas the yellow sides represent solid material. Smirnov, he proved conformal invariance of percolation on the triangular lattice. Smirnov was considering some simply connected domain D in the complex plane, and he fixed 3 boundary points, A, B, and C, in the boundary of D. Then he was considering a rescaled version of the triangular lattice restricted to the domain D, and he considered some arbitrary point Z, and he considered the event that critical percolation on this lattice has a blue crossing separating the points A and Z from the points B and C. And he was considering the probability of this event, and he was denoting this probability by P sub A superscript n of Z. So in this way, he defined some function P sub A superscript n on the domain D, taking values between 0 and 1. Similarly, he defined functions P sub B and P sub C by permuting the roles of A, B, and C. Then he defined a function phi sub n such that P sub A, P sub B, and P sub C define the coordinate functions. So this is a function defined on D, taking values in the unit cube. And then he was arguing that as the lattice size 1 over n is going to 0, then this function phi sub n is converging to some limiting function phi. And this limiting function phi is the unique conformal map from D to the equilateral triangle shown in the right part of the figure, such that the points A, B, and C are sent to the 3 corners of the equilateral triangle. So this result is what we call conformal invariance of percolation, because you can see that the limiting crossing probabilities only depend on this conformal map phi. Conformal invariance of percolation was first predicted in the physics literature as part of conformal field theory, and in particular, Cardy was deriving a formula for percolation crossing probabilities via non-rigorous methods. And Smirnov's theorem is a confirmation of Cardy's formula. By using the result on the previous slide, we get a natural embedding for planar maps, which can be viewed as discrete conformal. So I will describe this embedding in the context of triangulations with the topology of a disk, where we remember that triangulations are planar maps where all faces have exactly 3 edges. We fix 3 boundary vertices A, B, and C on the boundary of the planar map. And then we define counterparts of the functions P sub A, P sub B, and P sub C on the previous slide. So for example, we define a function P hat sub A, which is defined on the vertices of the planar map. And this function is defined such that P sub A, or P hat sub A, of V is equal to the probability that the percolation on the planar map has a crossing separating the points A and V from the points B and C. So this is an exact counterpart of the function P sub A superscript n considered on this slide. Then we define an embedding of the planar map via the formula in the indented equation, where the function PROJ sub t denotes projection onto the triangle in this slide. This gives us an embedding of the planar map, which I have made a schematic drawing of in the right part of the figure. And we call this embedding the Cardy-Smirnov embedding due to its origin as explained on the previous slide. So here I show again a schematic drawing of the Cardy-Smirnov embedded triangulation. So when we embed the planar map into the equilateral triangle, then we get a natural measure in the equilateral triangle. So I denote this measure by mu sub n. And this measure mu sub n is given by rescaled counting measure on the vertices. We say that each vertex has mass 1 over n, and we say that the measure of some subset of the equilateral triangle is equal to the mass of the vertices contained in this set. So in other words, mu sub n of u, where u is some subset of the equilateral triangle, is just equal to the number of vertices contained in this set divided by n. So n is representing the total number of vertices of the planar map. So it's very natural to do this rescaling, because then the total area assigned to the equilateral triangle will always be equal to 1, even as we send n to infinity. So in a joint work with Shin Sun, we prove that this area measure mu sub n is converging when the size n of the planar map is sent to infinity. So this measure mu sub n, defined on the previous slide, it converges in the scaling limit to some limiting measure mu. This limiting measure mu is the Liouville area measure that I was defining earlier. And remember that this measure is the measure which, heuristically speaking, has density e to the power gamma h relative to Lebesgue area measure. It turns out that the parameter gamma has the value square root of 8 over 3. So why is this result interesting? So it is interesting because it is the first theorem in the math literature which is giving convergence under conformal embedding for some uniform planar map model. So next, I want to present the convergence result in conformal topology for another planar map model. And this planar map model will be non-uniform. To explain how this planar map model is defined, I first need to introduce spanning trees. So here you see a planar map M with a spanning tree T. So a spanning tree is a subset of the edges which is connected, doesn't have any loops, and which is covering all the vertices. For example, the planar map in the figure is an example of a spanning, or the subset of edges shown in the figure in red is an example of a spanning tree. So here you can see one planar map M with 2 distinct spanning trees, T and T tilde. For an arbitrary planar map M, then we let n of M denote the number of distinct spanning trees that this planar map admits. For example, for the planar map in the figure, it turns out that it admits 32 different spanning trees, and therefore we have n of M equal to 32, and the figure is showing 2 out of these 32 spanning trees. Okay, so I will now define a natural, non-uniform model of planar maps. My model will be indexed by some parameter c that we often refer to as the central charge. So we sample a planar map M at random, such that for any fixed planar map little m of size n, the probability that big M is equal to little m is proportional to n of little m to the power minus c over 2. There are two different values for c that are particularly natural. So c equals 0 is natural, because if c is equal to 0, then on the right-hand side, we always have the value 1. So this means that each possible planar map little m has the same probability of being chosen. So in other words, the planar map big M has been sampled uniformly at random. So the case c equals 0 corresponds to the random planar map model that we have been considering earlier in the talk. The case c equals -2 is also quite natural. So if c is equal to -2, then the exponent on the right-hand side of the formula in the indented equation is equal to 1. So this means that the probability of sampling a particular map is proportional to the number of distinct spanning trees it admits. So equivalently, we can sample a uniform pair, m, t, where m is a map, t is a spanning tree on the map, and then afterwards we just forget the spanning tree t. More generally, when C is large, we favor maps that admit few distinct spanning trees, whereas if C is small, we favor maps that admit many distinct spanning trees. So why is this random planar map model interesting? One reason it's interesting is a prediction from the physics literature known as the DDK-ansatz. So this DDK-ansatz is saying that these non-uniform random planar maps, they should also be related to these LQG surfaces. And the ansatz is predicting that a planar map sampled as described on this slide, it converges in the scaling limit to gamma LQG, where the parameter gamma of the LQG and the parameter c of the planar map model are related via the formula in the indented equation. In particular, we can see from this formula that the case c equals 0 corresponds to gamma equal to the square root of 8 over 3, which is consistent with the theorem presented on this slide. And we can also see that this other special value of interest, c equals -2, corresponds to gamma equal to the square root of 2. Another reason this planar map model is interesting is the physics heuristic, which is saying that a planar map sampled in this way, in some sense, has been reweighted by the number of ways to embed the map in a c-dimensional space. Another reason the planar map model is interesting is that this number, n of m, it is related to several other statistical physics models on the planar map. For example, it is related to the Gaussian free field. And n of m, it also turns out to be equal to the Laplacian determinant of the planar map, little m. So finally, the planar map model is also interesting because of the Moulin bijection. The Moulin bijection is a bijection between planar maps with a spanning tree and walks on Z2. This bijection was discovered by Moulin already in the 60s, which is much earlier than the physics applications discussed higher up on the slide. So in a work in progress, we are proving convergence of tree-weighted random planar maps for the TUT embedding. So we are considering the planar map model considered on this slide in the special case when C is equal to -2. So we're considering this second special case of interest. And then we are embedding this planar map into the unit disk via the TUT embedding. So remember that the TUT embedding is this random walk-based embedding, which I introduced earlier. So then when we embed this planar map into the disk via the TUT embedding, then we get a natural area measure in the unit disk, which I denote by mu sub n. And as before, mu sub n is given by the rescaled counting measure on the vertices. So each vertex is assigned a mass 1 over n. So as the size of the planar map is going to infinity, then one can argue that this natural area measure, mu sub n, is converging to a limiting area measure. And again, this limiting area measure is the Liouville quantum gravity area measure. So now, which is the measure with density e to the power gamma h relative to Lebesgue area measure, but now this parameter gamma is equal to the square root of 2, as predicted with the DDK ansatz. So this theorem is the second convergence result under conformal embedding for what I call a combinatorially natural random planar map model. The first such convergence result is the theorem presented on this slide. But I want to emphasize that the proof of these two results is, so these proofs are very different. So you see that I use this phrase, combinatorially natural. So I use this phrase because before the theorem presented on this slide, and also before the theorem presented on this slide, Gwynn, Miller, and Sheffield proved a convergence result under a conformal embedding for another planar map model. So the result of Gwynn, Miller, and Sheffield is very nice, but the particular planar map model they consider is not as combinatorially natural as the planar map models we are considering here. So Gwynn, Miller, and Sheffield, they started out with an LQG surface. They discretized this LQG surface, and then they were defining a planar map from this discretization, and then they were proving that this planar map is converging under conformal embedding back to the original LQG surface. The proof in the Gwynn, Miller, Sheffield theorem is very innovative, and the proof of the theorem I'm presenting on this slide is using some ideas from that proof. As a byproduct of the proof of the theorem on the previous slide, we get that random walk on the TUT-embedded planar map is converging to 2D Brownian motion. So you can, what you see, look at here in the figure is a tree-weighted random planar map, which has been embedded in the unit disk via the TUT embedding, and then we do a simple random walk on this planar map. So it can, for example, be started from the vertex in blue. Here the map has taken 1 step, here it has taken about 20 steps, and here the random walk has been run until it exits the unit disk, or it hits the boundary of the unit disk. And this random walk will converge to the 2D Brownian motion in the scaling limit. And this is a quenched convergence result, so it is conditioned on the randomness of the planar map. Random walk in a random environment is a classical topic in probability theory, and the model I'm considering here, it's falling into the framework of random walk in random environment. The random environment in our context is simply this tree-weighted planar map, which has been embedded in the disk via the TUT embedding. So the general goal when studying random walks in random environment is to figure out under what conditions on the random environment that the random walk will converge to the 2D Brownian motion. And a particular challenge of the environment that we consider here is that it is highly inhomogeneous. So you can see that in certain parts of the disk, the density of vertices is very, very high, whereas in other parts of the disk, the density of vertices is very, very low. So in the remaining time, I want to say a few words about the proof of the theorem on this slide. So the starting point of the proof is the Moulin bijection. So the Moulin bijection is a bijection between planar maps with a spanning tree and walks on Z2. And this bijection is such that the size of the planar map is corresponding to the length of the walk. So if one has some random walk and one sends the size or the length of its random walk to infinity, then it will converge in the scaling limit to the 2D. And this, if this walk is on Z2, then it will converge in the scaling limit to the 2D Brownian motion. In the continuum, one has a similar correspondence as in the discrete between a 2D Brownian motion and a Liouville quantum gravity surface. So this correspondence was first discovered by Duplantier, Miller, and Sheffield, and this correspondence is a continuum counterpart of the discrete bijection. So more precisely, it is the case that if one has some instance of a 2D Brownian motion, then this is encoding some instance of a Liouville quantum gravity surface. So in this encoding, then each vertex v of the planar map is corresponding to some time t sub v for the walk. In the continuum, each time t for the Brownian motion is corresponding to some point p of t in the unit disk. So by using these correspondences, it's natural to define an embedding phi tilde of the planar map, which is such that phi tilde of v is given by p of t sub v. So this defines a natural function from the vertex set of the planar map and to the unit disk. And in the figure, this is a schematic drawing of an embedding, of a phi tilde embedding of a planar map. In order to prove the theorem on this slide, it turns out that it is sufficient to argue that this phi tilde embedding is approximately equal to the TUT embedding. So I will not explain in detail why this is the case, but this follows by using the correspondences illustrated in this figure. To prove that phi tilde is approximately equal to the TUT embedding, then it is again sufficient to argue that a random walk on the phi tilde embedded planar map is converging to the 2D Brownian motion. So here we have the planar map embedded via this phi tilde embedding, and we can consider a simple random walk on this planar map. In order to prove that phi tilde is approximately equal to the TUT embedding, it's sufficient to argue that the simple random walk is converging to the 2D Brownian motion. So this is sufficient to prove, as one can argue that this is sufficient to prove by using the close relationship between the TUT embedding and Brownian motion. So all we need to do is to consider this phi tilde embedded planar map, and we need to prove that the random walk converges to the Brownian motion. When doing this, we will be using an invariance principle or a theorem due to Gwynne, Miller, and Sheffield, which is explained in the third bullet point. So this is the theorem about random walk in random environment, which is giving some general condition under which a random walk in a random environment is converging to a Brownian motion. So before commenting on this theorem, I want to explain what the random environment is in our setting. So the random environment in our setting will be a local limit of what you see illustrated in this figure. We can look at the phi tilde embedded planar map. We sample a point from Lebesgue area measure in the unit disk. And it's possible to argue that if we zoom in nearby this point at the same time as the number of vertices of the planar map is sent to infinity, then we get the local limit. And the local limit will look something similar to the figure. So this local limit will be some infinite planar map, which is naturally embedded in the complex plane. And then it turns out that that the random environment defined by this local limit, it does satisfy the assumptions of the Gwynne, Miller, Sheffield theorem. So in order to apply the Gwynne, Miller, Sheffield theorem, it's necessary to argue that the planar map is sufficiently well connected, so there are sufficiently many vertices, sufficiently many edges. One also needs to argue that there are not too many very long edges, and one also needs to argue that there are not too many very high degree vertices. And one also needs ergodicity. However, the thing which is probably making this invariance principle stand out the most from other invariance principles in the literature is the assumption that the environment must be translation invariant modular scaling. So a number of invariance principles in the literature, they assume that the environment is translation invariant in law. So Gwynne, Miller, and Sheffield is actually not requiring this, but instead they're requiring something weaker. So they require that if we are translating the random environment by some constant, then if we recenter the environment at this other point, then they are not requiring that we get an environment which is equal in law to what we started with, but they do need that the environment is equal in law to what we started with after we have applied some random scaling. So it is exactly like a classical translation invariance, except that we're also allowed to do this random scaling of the environment. So it can be argued that this local limit that is sketched in the figure is satisfying these assumptions. So what is the key difficulty of the proof? So the key difficulty of the proof is to argue the existence of this local limit, and also to argue that this local limit is satisfying the assumptions of the theorem. So even establishing the existence of this local limit is very hard. Establishing the existence of the local limit is hard because the local limit is obtained by zooming in at some point sampled from Lebesgue area measure. If you look at the definition of this phi tilde embedding, then in order to define the phi tilde embedding, we need to have a coupling of a 2D walk and a 2D Brownian motion. And we also need to take a local limit of this coupling. So the issue is that at the point, or the time at which we take a local limit is a random time. And this random time is coupled together. It has a very complicated law, and it's coupled together with the 2D Brownian motion in a very complicated way. So that's why it's very difficult to take this local limit. But one can argue that this local limit does exist, and an important tool when establishing the existence of the local limit is a strong coupling of a 2D random walk and a 2D Brownian motion. Okay, thanks.
So thank you for the very nice talks. All the questions?
In this ongoing work, you mentioned, I think you mentioned the central charge has to be some specific value. Can you comment on why it's that?
I could actually repeat the question because I can't hear it very well from here. Or if, yeah.
Oh, yeah. In your ongoing work, does you fix your central charge value, like to a specific value?
Maybe it's easier if you don't use the microphone, actually.
For this new work, you have a specific central charge value.
Yeah.
And why is that? Why not taking other values? Can you comment on that? Thanks.
Yeah, so I can comment a bit on that. So first of all, I can say that actually big parts of the proof, in principle, actually should work also for other central charges. But I can comment a bit on why I'm considering this central charge in particular. So the thing is that so this central charge is corresponding. So it is the case C equals -2. So it means that the planar map has been reweighted by the number of distinct spanning trees it admits. So as explained in the slide, it's equivalent to picking a uniform pair consisting of a map with a tree and then forgetting about the tree. So the thing is that these planar maps with spanning trees, they are very nice. So one nice property of them is that they are in bijection with walks. So this is the Mullen bijection. And this Mullen bijection is playing a very important role in the proof. Planar maps with spanning trees are relatively easy to understand because they are in bijection with walks via the Mullen bijection. It is actually the case that for certain other central charges, one also has similar types of bijections. So if one has a similar bijection or a bijection which is similar in spirit to this, then in principle the proof may also carry through.
Questions?
Thank you for the talk. Two short questions. So firstly, if one would want to study scaling limits of any stochastic process like with Schramm and so on, could this be done in conformal topology? And is there bijection, one could say also here? Could conformal topology help also in study of scaling limits of any of these? And secondly, related, based that this takes place in complex plane, could tools of complex analysis, also other tools, be used to study scaling limits and other properties in conformal topology? Thanks.
Okay. Again, I actually had some trouble hearing it. Yeah, maybe it's easier if I just come a bit closer and then you can just say it without the microphone.
So maybe
Yeah.
Okay. So firstly, could any scaling limit of a stochastic process be studied? It is commonly studied under different topologies like Skorokhod and so on. Could it be studied under conformal topology? What would this topology bring to the study of scaling limits? And I hope you hear.
Okay, so I think I get the question now. So the question is, so in my talk, I'm studying, taking a conformal scaling limit of random surfaces, and the question is whether one can consider some kind of conformal scaling limit of other
Just the
processes.
general scaling limits could study in conformal topologies.
Yeah.
Had to study in other more common topologies.
So the question is whether other processes can maybe also be, one can define some notion of conformal topology also for other processes. So I would say not necessarily. So I would say that the thing is that the conformal topology somehow makes sense in the study of surfaces because one can define what it means that the surface has a conformal structure. And for some general other process, it's not really clear exactly how one would do that. Yeah.
And just secondly, based that this takes place in a complex plane, naturally,
Yeah.
Could other tools of complex analysis, there are tons of them, also be fruitfully used in future to study anything, any property in conformal topology, in Liouville quantum area measures, Liouville measures, and similar properties and objects?
I'm not sure I've fully understood the question.
Could you use other tools from complex
Other tools
analysis
from
in the future? Say you mentioned counting measure.
Yeah. If one can use other tools from complex geometry. Of course, there is a chance. So I don't know exactly what that would be, but of course, so these results that I'm presenting here, they are so the proofs are very specific and they build on a huge amount of machinery, and it would definitely be very nice if one had some proof which is using other methods, for example, which are, for example, not based on this whole machinery. I don't know exactly what this would be, but for example, if you look at this last problem that I was presenting, so it's essentially a question about. It's closely related to random walk in random environment, and somehow the way I'm analyzing this walk is by using this whole machinery, and it's one could ask whether one can find a more elementary proof of this fact, and maybe tools from complex geometry could play a role there. But I don't know exactly what these methods would be.
Thanks.
Maybe a quick last question, or we keep the questions for the break. And if you want to look at the beautiful 3D version of the planar maps, please come and see Nina. Okay, so let's thanks again, Nina, for this very nice talk.
Also for you, Nina, we would like to give you a small present, and thanks a lot for the talk. This is the perfume we make in the university in Bochum, Rupp University, and as we always say, we are the only university in the world to do their own perfume.
Yeah, thank you very much.
Okay, so welcome to this medallion plenary lecture. It's my great pleasure to introduce the medallion lecturer, Moulinat or Mouli Banerjee. Mouli received his PhD from the University of Washington, and before that, he actually got his bachelor's and master's in statistics from the ISI in India. After his PhD in Seattle, in Washington, he moved to the University of Michigan at Ann Arbor, where he stayed until today, now as professor of statistics. Mouli has very broad interests, research interests also, and he has done foundational work in the theory and analysis of what I would call modern statistical methods and algorithms. This includes topics such as non-standard asymptotics, empirical processes, shape-restricted estimation, threshold and boundary and change point estimation problems, and even more. In addition, he has also been involved in interdisciplinary work in astronomy. Needless to say, Mouli published in the best journals in the field. Mouli has also done a great amount of service to our community, especially also as associate editor for many journals, including the Annals of Statistics, JASA, Bernoulli, and he is currently the editor-in-chief of Statistical Science, where he had this very good, great original idea to promote short communication, short articles, which is really a new thing which he drives forward. Mouli is a fellow of the IMS and a fellow of the ASA. Apart from his statistical pursuits, he has an avid interest in many other things, and I mention here classical music, fine dining, literature, philosophy, and poetry. And he even published a new translation of the Rubaiyat at Omar Khayyam. Very impressive, Mouli. Each year, IMS nominates 8 medallion lecturers in fields across its subject range. The award of a medallion signals the honor inherent in being selected to deliver one of these lectures. IMS awards the medallion to Moulinat Banerjee and invites you to present a medallion lecture entitled Estimation and Inference for the Average Treatment Effect in a Score-Explained Heterogeneous Treatment Effect Model. Please come on stage.
Is it working? Yep. Okay, great. Well, thank you, Peter, for that very fine introduction. And I'm deeply privileged and honored to be selected to give this lecture. And of course, I mean it. It also seems to be a good place to acknowledge some debts of gratitude very shortly, starting with my parents, the Indian Statistical Institute, my advisor, John Wellner at the University of Washington, 2 colleagues who were not in the same department with me, but who played a pretty integral role in my early development as a researcher. These are Ian McKegg of Columbia University and Michael Kosorok, who's seated there from UNC Chapel Hill. And if you don't know who Michael is, he's the only person who looks like a sage in this audience. I should also acknowledge the brilliant colleagues at Michigan that I've had over the years, starting with Michael Woodruff, now departed, George Michailidis, who's at UCLA, and more recently, Yakov Ritov and Yukai Sun, my younger colleague who teaches me all the modern things that are going on in the field. So let's have a little bit of fun now. Okay. So those are the primary actors. So just put pictures of all three of them. So that's the honcho. You know who that is. The word honcho is actually derived from the Japanese word hansho, which means leader of a group. And then the honcho, of course, is supported on the shoulders of, well, to quote Newton, giants, but that's just a joke. Though you have Yankee Ritov there, the deep guy, who's taking aim at some complex statistical conundrum with his characteristic ease and aplomb. And then this is Zeb Mukherjee, who's at Boston University now. He was a joint student of mine and Yankees. And if you don't know what Young Turk means, you can look it up. OK. So we're going to talk about endogenous treatment effects primarily in this talk. And the work will basically spin off what is called regression discontinuity designs. So what's a quasi-experiment? Well, it's an experimental design where you estimate the effect of some treatment, where the allocation of treatment is not random, but is based on the characteristics of the subjects. And you see, when you do randomized treatments, it's easy to estimate treatment effects because you can do easy comparisons of averages of the responses, which you're trying to optimize between treatment and control groups. But then, if you assign treatment in a way that depends on the characteristic of the subject, and the characteristic intrinsically also can influence the response you're optimizing for, then the confounding bug bites you, and it's very difficult to isolate the treatment effect from this intrinsic characteristics of the subjects, which could also be driving the response of interest. And one related area that has received a lot of attention in the econometrics literature, and I guess we think this is the first reference to this area in scientific analysis, is it's the regression discontinuity design problem. So there are various examples where treatment is assigned based on characteristics of the subject, which themselves could influence the value of the response down the road. So this is a famous example where the special college preparatory program of the Cincinnati Board of Education had a positive effect on the retested students in terms of their mean academic achievement. And then these kinds of applications also come up all the time in epidemiology and public health. For example, sometimes you're assigning treatment only to the people who are at the greatest risk. So they're the ones receiving the new treatment or prophylaxis. And you're trying to basically improve their responses, but the fact that they are very high-risk patients intrinsically means that something is wrong with them, and this could show a mitigated treatment effect if you just try to estimate the treatment effect naively. So here's a schematic diagram that's going to kind of try and explain what's going on. So you have the response, that's subsequent academic achievement. You have treatment, which is a scholarship. And the scholarship is given, of course, if you cross a certain score in some sort of merit test. So now you have these native abilities of these individuals. Now, if you write out a model, these are unmeasured native abilities which go into the residual term. Now, we know that those are going to have an effect on the response, which is the eventual academic achievement or eventual grades or whatever. But then the problem is that there are these arrows going on. Now, there is a good arrow and there's a bad arrow. So what's the bad arrow? The bad arrow is the short arrow. What it's saying is that the native abilities can themselves influence the treatment, because if you have higher intrinsic, say, academic skills, you're going to probably score higher on the selection test, and then you're going to get the treatment. But then if you have higher native abilities, you're eventually also going to get higher grades. So now the effect of treatment has been confounded by this intrinsic propensity to get, to do better in the group that did receive the treatment. And so that creates the confounding problem. Now, what will alleviate the confounding problem? So if you forget the long red arrow, this is basically what leads to confounding and endogeneity. So we will draw the long arrow, and that will be an added equation that will help us estimate treatment effects more efficiently. And let's see how that works. So it's very customary to set these things in a potential outcome framework. I mean, we'll just do this to kind of fix ideas. So the response of the ith individual is basically of the form yi1 if q is bigger than tau. So q is the score on the scholarship test. Tau is the threshold at which you give the scholarship. And yi1 is the response under treatment. yi0 is the response under control. So these are, say, the future grades, okay? And so for each individual, you observe yi1 if qi is bigger than tau, that is, they get the scholarship. Otherwise, you observe yi0. Of course, you don't observe the same as, both values for the same individual. Now, you can define the conditional mean functions, mjq, as expectation of yj given q. So for j equals 1, what this means is that if you gave the treatment to every single person who scored q on the test, what is the conditional expectation of their future achievement given q, okay? So this is typically unknown. And so is m0. And expected y given q has this dichotomous form. That's immediate. It's m1q if q is bigger than tau, and m0q if q is less than tau. And it turns out that you can't really estimate m1 and m0 fully, but you can actually estimate them at the threshold tau. And that is the whole notion of regression discontinuity designs. M of q has a discontinuity at tau, and at that point, it is possible to estimate the treatment effect. And this is a problem that has generated enormous interest in the econometrics literature. People have been working on it ever since this, that paper was, it may have become more popular at some point. I don't remember the exact history. Nevertheless, let's try to take a look at how we estimate the treatment effect here. So we define alpha naught to be the expectation of y1 minus y0 given q equals tau. Then we split, simple algebra. Now you write expected y1 given q equals tau as a decreasing limit of expected y1 given q equals t, as t decreases to tau. And then you subtract from it expected y naught given q equals t, and you take the limit as t increases to tau. So we obviously have some mild continuity assumptions to make it work. But now, as t is bigger than tau on the left, y1 is y. As t is less than tau on the right, y0 is y. So what you get to be alpha naught is the decreasing limit of mt as t decreases to tau minus the increasing limit of mt as t increases to tau. So you can see that it's a local parameter, right? It's a local parameter that's focused around the behavior at tau. And so what you really can do is you can estimate it non-parametrically in a neighborhood around tau. But you cannot really use all of your samples to estimate this quantity. And that makes sense. It's a local phenomenon. Now, the whole question is, should we always worry ourselves about estimating the treatment effect at the boundary? So that's the whole question. Now, this is a big paradigm in econometrics. In lots of applications, you are really interested in what happens away from the boundary, right? I mean, people who are at the threshold on the right may not be different from the people on the left. So basically, you want to see if the treatment is really useful for other people as well, global effects. OK, so there is a similar model that was explored by a bunch of authors, and my good friend from Michigan, now at Princeton, Matthias Cattaneo, is one of the authors. And here they write a similar model, but now with covariates. So you can see the model. I don't need to spell out the full details. It's basically you have two functions, m0q to the left of tau, m1q to the right of tau. You have some exogenous covariates, which are providing more information about the response. And you have these errors, these new i's. And the whole point is that these errors are not exogenous, okay? These errors capture native abilities, and q also is affected by native abilities, so the expectation of nu I given qi is not equal to 0. And here is the problem. The problem is, you see, maybe there is some correct treatment effect which I denote by m0 and m1, but that's not identifiable, because I can just write nu as its conditional expectation given q plus a residual, right? And now that is a function of q, right? And I can absorb the whole thing into m0 and m1. So these functions, m0 and m1 by themselves are not identifiable, right? They're confounded with the effect of expectation of nu given q. However, the difference is estimable at the point tau. And that is what the econometricians are primarily estimating. So as again, under mild continuity assumptions, you can show that alpha naught, the treatment effect at tau, is m1 tau minus m0 tau. And there are ways to estimate this using non-parametric techniques. So that's good. OK. As you can expect, how would you, this is a non-parametric function estimation. You're trying to estimate the limit of mt as t increases to tau on one hand, and the limit of mt as t decreases to tau on the other hand. So you get this natural estimator alpha hat, where on the left you take a kernel smooth average of the y's for q's bigger than tau, and you do the same thing for q's to the left of tau. You take the differences, and under the usual conditions, now if you've dabbled to a certain extent in even basic non-parametrics, you can see that you would expect a result like the one that's written down in blue. Okay? So you get a non-parametric rate of estimation. There are some bias variance issues, but we don't need to worry about it. The crux is you get a non-parametric rate of estimation. So let's boil ourselves down to the simple model. So I'm just going to have an effect for q bigger than tau. And let's assume that the effect to the left of tau is 0. Now, as I said, why should we just concern ourselves about estimating global effects? I'm sorry, local effects. Let's try to estimate global effects, can we? So suppose I'm interested in the average treatment effect on the treated population. So it's the expectation of MQ conditional on q bigger than tau. So it's the average of the MQs for the treated population. Now, this is an average, right? As soon as you start taking averages, which look like integrals, they become smoother functionals of the distribution. And convergence rates should improve, right? So can you estimate it at rate root n? It turns out that you can't. Based on these kinds of models, there is no way you can estimate the average treated effect at rate root n, even though these are smooth functionals. And why is that the case? Well, I'm going to make life simpler for you. I'm going to talk about an extremely simple problem where m of q, the effect of the treatment, okay, when q is bigger than tau, is completely homogeneous. So it's equal to alpha naught. Okay? And while I say heterogeneous treatment effects in the title, the bulk of this talk will be about homogeneous treatment effects. And later on, I will talk about heterogeneous treatment effects. So, okay, so MQ is identical equal to alpha naught. Very nice. The local and the global effects are the same. We write GQ as the conditional expectation of nu given q equals little q. That's basically that conditional expectation, right, that messes things up for us. And now I can write yi as alpha naught times indicator qi bigger than tau plus gqi plus epsilon I, where epsilon I is an exogenous error because I've taken off the conditional expectation. So this is now a standard regression model with an exogenous error epsilon. Okay? The reason why you cannot estimate alpha naught at rate root n, despite this being a partially linear model, is because the covariate in the non-parametric part of the model qi is explaining indicator qi greater than tau completely. So the conditional variance of indicator qi greater than tau, sorry, it should be tau, not a t, given qi equals 0. But hey, that is just the efficient information for alpha naught in the model, up to a constant, which means that the information bound is infinity, which means you cannot have a root n estimate. So if I just use these kinds of equations, I'm never going to be able to get a root n estimate. And if I want to estimate, and my point is we want to estimate the average treatment effects. We just don't want to estimate the effect at the boundary, which, and Yankee is more militant about this than I am. He actually thinks, why is regression discontinuity design even interesting? And, but let's not go into that. But my point is we're looking at a different target. And there is no way that these models can, this particular equations can help you get a root n rate. But you can do something that can help you. And that has to do with the longer arrow that was drawn. Okay, let me forget this pause business. I never am a big fan of it. So I should thank Deb Mukherjee for actually creating the slides originally, and then I fine-tuned it quite a bit with his help. Okay, so the same issue arises in the more general model. So now we have yi equals alpha naught if q is bigger than tau, plus x transpose beta naught. The x's are measurements on the individuals. These can be thought of as exogenous covariates, plus, again, that endogenous error. Now, here is the thing. It's not that we just observe indicator q bigger than tau. We know the scores of these people, right? And we are happy to model. So what are the Qs once again? The Qs are the scores they got on the merit test, based on which they got the scholarship. The Y is the score they got when they were retested, right? So future performance. Now, if we are happy to model Y in terms of covariates, there is no reason we shouldn't think about modeling Q in terms of covariates either, right? So why don't we use the X's to model the Q? We can even use more covariates to model the Q. The whole point is, why don't we write down an equation to model the Q? Okay? And then we'll have two equations, and that actually helps us a lot. Okay? That saves us from, the curse of confounding. So we start with a joint model. We're keeping our model exceedingly simple right now. This is one of the things the econometricians didn't like. The work went around and bumped around in a few journals, and every time we could see that it was going to the econometricians. They didn't like the approach, and eventually it's being published in a good statistics journal. The statisticians seem to like it more than the econometricians. I'm not trying to prime you or anything, but that has been our experience. So let's start with the linear model. So the first equation, yi equals blah, is the original equation. That's what we've been working with. We now add this new equation. Qi is xi transpose gamma naught plus eta I. So work with a simple linear model. Everything is in low dimensions, nothing fancy. Okay, as classical as you get. And we assume that eta has we assume that xi is independent of eta and ui. This is not strictly needed, but for the purposes of the talk. We assume that eta and nu are correlated arbitrarily, and we assume that expectation of eta is equal to 0. So the second equation that describes qi is a proper regression equation. Eta I is exogenous, nu I is endogenous. And if you ask, well, how do you know some more covariates might not be useful in modeling a Q? This is not a problem. You can actually add as many covariates as you want to X, okay, in the Q equation. So you could have even a different set of covariates in the Q equation. It wouldn't really matter. But the point is we have two equations, one which models the Y's and the other which models the Q's. So all we are saying is that the score, the Q that determines the scholarship, can also be explained by background information and native abilities, okay? If Y can be explained by that, so can Q. This is certainly not a huge leap of faith, right? It's perfectly rational. And note that we have endogeneity because expected nu given Q is not equal to 0 in general. So the first equation is not a proper regression model. I can't use linear regression. Okay, so we're going to work with these two equations, and let's see what that buys us. Now, there is some work in broadly similar vein that was considered by some econometricians, but in the interest of time, I will not worry about this so much. But whatever's being done here is sufficiently distant from what we are doing and has nothing to do with this notion of regression discontinuity designs. So I'm going to skip it for the moment. So how do we now proceed? Well, we take the first equation. We write the first equation in this way. So what we do is, the first two terms are the first two terms. We just take the nu I, the endogenous error, and we split it as f of eta plus epsilon, where f of eta is simply the expectation of nu given eta. And this is a non-trivial function. This is a non-trivial function because nu and eta are arbitrarily correlated. Nu and eta both represent aspects of intrinsic ability, so they are arbitrarily correlated. Now, if an oracle told you eta, you're in great shape. If an oracle told you eta, you would be in great shape, because now you would have a semi-parametric linear model where the covariates corresponding to the parametric part, namely indicator qi greater than or equal to tau and xi transpose, right? The two covariates corresponding to the parametric parts of the model are the indicator and xi transpose. Now look at the conditional variance of that given eta, okay? Eta does not fully explain those covariates. So now you actually have a positive definite conditional variance, which means that the efficient information is finite, which means that the information bound is finite. Sorry, which means that the efficient information is not 0, and which means that the information bound is finite, and you can expect to get a root n rate, okay? So there is hope here that we can get a root n rate if an oracle tells us eta. But of course, there are no oracles around to tell us eta, so what do? We estimate eta. And how do we estimate eta? The residuals, we use the second equation to estimate eta, right? Okay, so we are going to estimate eta. We don't know the etas, so once again, if we go back, we don't know the etas that the oracle knows, But for any given individual, we can estimate eta, and we can estimate eta using the second equation, qi equals xi transpose gamma naught plus eta I, if we are able to estimate gamma naught. But we can use least squares to do it. Right, so how does the thing proceed? And these are probably the slides in the talk that will have the most equations, and I will try to go through them. There's not too many technical details, just to get a sense of how we operationalize the procedure. So you have a sample of size n, okay? And you need a little bit of sample splitting to make things work, so let me just walk you slowly through it. So you have a sample of size n, chop it up into 3 equal parts, or approximately 3 equal parts, okay? Take the first part and estimate gamma hat from it, okay? Simple least squares estimate. Take the first third of your sample and estimate gamma hat via a simple least squares procedure, okay? Now take the second 1/3 of your sample and estimate the residuals eta hat I for those subsamples, right? Just by that simple equation. And then you expand the first equation, f of eta, around f of eta I. So you remember, if you go back to f of eta I here, right? You just expand it, okay? Using eta I hat, so that's a simple Taylor expansion. And you have a residual, which is in blue. Now, the thing is, that residual, it's easy to show that it's of the order 1/square root of n. And that's kind of big, because you know that if I'm going to estimate alpha naught at rate 1/√n, and if I fit the model by forgetting the residual, the error that I'm leaving out is of the same order, right? Normally, you can ignore terms which are of smaller orders. So this is not a great strategy for estimating alpha naught. But for the moment, we don't care. At this point, we want to estimate the non-parametric part of the model. The non-parametric part of the model, of course, converges at rate. It cannot converge at rate √n. So I can ignore that residual for estimating the non-parametric part of the model. So I'll first estimate f and f prime, okay? So how do we do it? Well, at this point, we're using standard partial linear model theory, okay? We expand f of eta hat I in a B-spline basis. And I really don't have time to explain B-splines, but I think many of you know what they are. They're a particular set of splines which have supports that kind of keep shifting, and they form a basis. So we can expand the f of eta hat in terms of this B-splines as a linear combination of B-splines. And the number of splines we actually use has to do with basically what we do is we take a compact interval, we partition it into essentially k subintervals, and then the points that define the partition become the knots of the spline. So anyway, so now, once we've done that, we can run a full regression model to estimate alpha naught, beta naught, delta 1, all the way up to delta k, okay? So this just involves running regression, right? We have a regression model here. So we're going to run a regression model. And the eta hat i's are known, right? Remember, we estimated the residuals. So we get our f in terms of the coefficients, the delta hats that we find by fitting the least squares, and we estimate f prime, and then we estimate f hat prime, okay? And we need to choose k carefully. So basically, at this point, we've estimated f hat prime. Okay, but finally, we need to estimate alpha naught, so we need to do a little more. So what we do to estimate alpha naught is, remember we did a one-step Taylor expansion before, now we do a two-step Taylor expansion because we want a residual that's of smaller order. So this is the two-step Taylor expansion. And the thing about the two-step Taylor expansion is that if you look at the term in the box, that term is of order 1/√n. Sorry, 1/n. That's a very small term. You can ignore it, okay? You can ignore it to all intents and purposes. That's a very small term because it has the eta hat I minus eta I squared. And so now you have an equation. Now you have an equation. That's the last equation written down there. And notice that f prime was estimated previously, right? F prime was estimated previously. So we do another expansion. And there's a particular residual, but that residual is actually ignorable. And I don't want to go through any more details there, but basically, there's a little bit of more massaging of these equations, and this is the final equation you get, the one right at the bottom. And that term just before the epsilon I is actually linear in xi f hat prime eta hat I. And so at this stage, what you do is you've given yourself a partially linear model with the right properties, and you can go ahead and estimate alpha naught. So that's really everything there is to it. So at this point, you end up with the equation right on top, and now you get a nice partial linear model which has non-vanishing efficient information, and you can now refit f with the spline basis again and get an estimator of alpha naught. So all we've done is basically I've tried to show you how to operationalize the procedure, because we don't know eta and we have to substitute it by eta hat, and we have to keep track of the errors we incur by these kinds of substitutions, so we have to be a little bit clever about this. Okay, so let's not worry about sample splitting. I kind of, already mentioned sample splitting, because otherwise the estimator becomes extremely difficult to analyze. And so once you do everything and put everything together, what you get is an asymptotic normality result. You can show that root n alpha hat minus alpha naught converges to normal 0 sigma squared, where sigma squared has some complex form, which we don't need to worry about here. And it's semi-parametrically efficient under normality of epsilon. This is something we can prove, but of course you may not have normality, but that's at least something satisfying. There's a little bit of a nuance to this result, because to make this procedure work, you really need to truncate the residuals. So in some sense, this variance sigma squared depends on the truncation level, but let's not worry about that. The take-home message is the use of the second equation enables us to get over the regression discontinuity design hurdle, okay? And if you want to actually get global treatment effects, estimate global treatment effects in an efficient manner, you really need to take your running variable, as the econometricians would call it, in this case the score on the scholarship test, and you need to try to model it, okay, to get around this confounding that is intrinsic to the regression discontinuity design formulation. So now the apprentice enters the picture. So what I presented to you thus far is this work, which is almost about to appear. I don't want to say the journal's name. It's really a very minor revision. The editor and the AE think we're not paying enough attention to this little typos. So right now we're just making sure that they said we don't want to send it back to you again and say correct typos. So we are kind of taking our time on it. So that's essentially done. But what we want to do is we want to extend to heterogeneous treatment effects, right? Because this is a simple model, and no one really believes that treatment effects are homogeneous, right? And so Kevin Wibisono is not my student, but he took a theory course from me and then wanted to work with me and Yankee on something. So we thought he would be a good person to do some work for us for the second project. Or maybe there'll be a third, I don't know. He's actually now fascinated by neural networks and LLMs and works with somebody else in a department, but he's also interested in this, but he's not a PhD student. So, heterogeneous treatment effects, which was really what this talk was supposed to be about. So let me say a little bit more about heterogeneous treatment effects, and I think I actually have some time. I went through the slides faster than I thought. Okay, so when we do heterogeneous treatment effects, we want to replace that alpha naught by something that varies, right, with respect to other things. And so the most general thing is you let your effect depend on both xi and eta I. So everything is the same as before, just the alpha naught changes to alpha naught of xi comma eta I. It could also be alpha naught of eta I, alpha naught of xi, but that's just the more general formulation. Remember, because q is a function of x and eta, this also covers the case where the heterogeneous treatment effect is directly a function of qi. Now, what's our parameter of interest? Well, our parameter of interest, theta naught, is the conditional expectation of alpha of x comma eta, conditional on q being greater than or equal to tau naught. It's the usual thing, right? That's the average treatment effect. And we may also be interested in estimating alpha dot. Of course, that itself is only going to be estimable at slower rates. So let me just talk about a slightly simpler model. I mean, I could have talked about the model where I just introduced, but for the moment, assume that alpha naught just depends on eta. And so now we have these two equations, okay? Nothing's changing. I'm just changing the nature of the heterogeneous treatment effect. Now, you could say, well, I don't really know. This alpha naught could be a fairly complicated function. We're going to assume it's smooth, but it's going to be a fairly complicated function. What if I'm agnostic and just fit a constant treatment effect, right? So let's fit a misspecified model. OK, there is some weird function that dictates the treatment effect. Now, I want to make life a little bit easy for me, so I'm just going to fit a constant treatment effect. OK, so I'm just going to pretend that I have a homogeneous treatment effect and fit it. So in that case, what are we estimating? What population parameter are we estimating? Now, it turns out that you actually estimate a weighted average of these alphas. And the weights are provided by a non-negative function, p eta, which essentially depends on the information for alpha in each eta stratum. But why is this useful? Well, you could first think of it as some sort of a weighted treatment effect, if you like the weighting function p eta. But even if you don't like it, think about testing that this is equal to 0. OK? Suppose you fail to reject the test. Now, if you accept the null hypothesis or fail to reject the null hypothesis that this is equal to 0, well, note that this is equal to 0 if and only if alpha is identically equal to 0, so long as it's continuous. So even by fitting the misspecified model, you can get a valid test for testing that the function alpha is identically equal to 0. Okay? So even if you fit the misspecified model, you can get a valid test for testing that the global treatment effect is actually equal to 0, provided this alpha function is continuous. So that's one nice thing about it. But of course, we may be wanting to do something more. We may actually be wanting to estimate this, this proper treatment effect, alpha x comma eta. Well, the conditional expectation of it given that q is bigger than or equal to tau naught. So one way to do this, OK, I have 10 minutes, I guess. It's 5:10. Peter, can you just, by my clock, it's 5:10? Yeah, OK. So one way to do this is by using what's called a matching algorithm. And this kind of matching strategies have actually been used by other authors who've dealt with these sorts of problems. I think we used a paper written by Tony Kai and Larry Brown and someone else. There are various matching strategies. Now, the use of the matching strategies is helpful because in many cases it can, you can circumvent estimating the non-parametric treatment, the non-parametric function f that we had to estimate before. So how does the matching algorithm work? So right now we are working in the setting of a heterogeneous treatment effect. So we no longer have a constant treatment effect alpha naught. Our treatment effect depends on both x and eta. So we have alpha naught of x comma eta. So you partition your sample into 3 subsamples of roughly equal sizes. The first step is what I told you before. The first subsample is used to estimate this gamma hat guy, OK? This first sample is used to estimate the gamma hat guy, which we need. OK, once we've estimated gamma hat, we can compute estimated residuals for all samples in the remaining part, right? Because eta hat I is qi minus zi transpose gamma hat. So now we have the estimated residuals for 2/3 of the data, which will now be used for different purposes. So now you move to the second subsample. So, and denote the control observations in the second subsample by I2 super C, C for control. Order the residuals, eta hat I, in the set I2C, so for I in I2C, and let eta hat bracket I be the corresponding ordered statistics, and then let x bracket I, y bracket I be the induced order on the corresponding xy pairs. So essentially what you do is you're ordering the observations by the ordering on the residuals, OK? And then, having done that, you get this first order difference as delta y bracket I. So delta y bracket I is y bracket I minus y bracket I minus 1. And delta x bracket I is x bracket I minus x bracket I minus 1. Now, it is not very difficult to show that if you regress the differences of the y's on the differences of the x's, and set beta hat to be the coefficients corresponding to this regression, that gives you a consistent estimator for the beta parameter. This is the effect of the covariates. Okay? The effect of the non-parametric part is essentially eliminated because you see the ordered residuals are very close to each other. Okay? The ordered residuals are very close to each other because they're ordered statistics from a common distribution. So they are within a 1/n range of each other. So basically, at this point, you've gotten an estimate of beta hat, which is good enough. Now you go to the third. Now you go to the third subsample, and for each observation in the treatment wing, you find its nearest neighbor in the control wing. Okay? And so C sub I is basically the index of the nearest neighbor in the control wing for the ith observation in the treatment wing. And then you can show that theta hat, which is the global treatment effect, is consistently estimated by this equation here. So what do? So for each I in the treatment wing for the third subsample, you look at yi minus xi transpose beta hat. And from that, so that's in the treatment wing, and then you subtract off yci minus xci transpose beta hat. The ci is the nearest observation in the control wing. And that will give you a consistent estimator of theta naught, and you can show that it's actually root n consistent with some asymptotic variance. Okay, so that's more or less completes the technical part of the talk, but I just want to talk about some relaxations because this is important. Now, a very legitimate criticism is that we've been completely working with linear models. By the way, there's also a high-dimensional version of this problem where you can let the covariates be high-dimensional, but that just becomes extremely ugly in terms of calculations. You can still get a result. So, but I'm not really, so that part is really not that important in my mind. But the thing is, we are modeling relations linearly, right? And people generally, a lot of people don't like it, right? But that's fair game, We can do better things than linear models these days. So what happens if the relation is nonlinear? So I assume that Q was a linear function of the observed covariate Z. Well, in our model, the Z's are the X's, but basically we could have used even more covariates to model the Q. Now, we believe that, at least in the homogeneous model, even if you fit a non-parametric function to describe Q in terms of the covariates, you may still be able to get a square root of n rate, at least in low dimensions, and by using certain non-parametric techniques. Now, it's not clear what would happen. So what if I had a really, really high-dimensional covariate Z, or X, which I was using to model Q? Or what if I use some really complex deep neural network model? There are all sorts of questions you could ask. So there is this issue that you could non-linearize the second equation, and what would happen at that point is still an open question, and I think there's certain interesting things to be done there. And then you could ask, well, how about nonlinearity in the first equation, right? The first equation is a linear model, right? It's alpha naught times indicator Q bigger than or equal to tau plus x transpose beta naught, and so on and so forth. Well, it turns out that what you can do or what you cannot do is quite heavily dependent on what kind of model you fit. But there is some hope that, that we might be able to get square root of n rates for the average treatment effect under certain conditions. But even if we can't, it's interesting to explore to what extent and with what rates you can estimate this global treatment effects when you relax the linearity assumptions. And that brings me to my last slide. So what did we do? So the main idea here was, as you can see, the mathematics is it needs a bit of work to get these things. And some of these calculations can actually become quite a bit ugly. But in terms of the mathematics that we've done so far, I mean, this is essentially we've used a set of very standard techniques. But I think the main contribution of this work is that, or these works, is that it gives you a way to get at a global treatment effect in a broad variety of situations that have been of considerable interest in the economics or the econometrician community, where it seems that there are very natural questions about global treatment effects which appear to be, incapable of being addressed by the classical regression discontinuity design paradigm. And and of course, econometricians are fairly hard to convince sometimes. My wife is an econometrician, so I can say this. But on the other hand, they also have very constructive criticisms about things, and they're very wary, So, and they worry more about misspecification probably. So I don't know. But it seems there's certain things can be done which might be potentially interesting. And there are categorical variables, so I think we should be able to deal with categorical variables. And the variances are extremely ugly. The variances that come up for these limit distributions are extremely ugly. So we've been using Bootstrap, and it's been working well empirically. But if you want to try to get the Bootstrap to, trying to prove anything for the Bootstrap is going to be even more ugly, because the actual asymptotics can get a little bit, dirty, so to speak. And then, of course, the main thing is how can we explore relaxed models, or what's the potential of exploring relaxed models in this type of a setup? So anyway, I'm glad I managed to finish before 5:20. It's 5:18. I thought I'd run out of time. And I hope at least there was a little bit of stuff about the talk. Like, you got the main message. I know maybe the equations seemed to me that they were not, okay, it was just 4 pages of equations, but once you start presenting during the talk, say, okay, well, maybe I wrote down too many equations. But I hope you at least got the message as to what we are trying to do and how it's different from what's being done so far in economics, and why there is some potential. And thank you very much once again.
Thank you very much. We have a bit time for some questions or comments. Please raise your hand if you want to say something.
Richard. I'll go close to Richard because
for the others he should.
Oh, that's right.
But maybe go close.
Yeah, for myself.
Well, I have a little question about one of your very early slides. So I'd like to see the one with the diagram with the arrows, the black arrows and the red arrows.
Oh, the arrow diagram. Okay.
And you remember there was a short arrow and a long arrow.
Okay, hang on.
So I enjoyed the talk, by the way. But
Thank you.
I started worrying about your diagram and. Yes.
Yeah.
What about an arrow from background information to native abilities? Or are you going to assume that,
very good.
I mean, or maybe you dealt with it later, but I didn't notice.
Background information to native abilities arrows is actually a very good point. Yes, if you start drawing those arrows, the entire paradigm changes, because then, then you can see what trouble we are going to get into, right? Because as of now, well, we assume nu eta was independent of x, but you can relax it to conditional mean zero assumptions. But if you start drawing those arrows, those conditional moment assumptions being equal to zero won't be.
So you're basically assuming that you're sort of defining native abilities by stating that they are independent of the background information.
We don't need independence, but we need some conditional mean zero restrictions.
Oh, yeah.
And they're not that different, yes. How do you differentiate one from the other? But yes, that's definitely true. And if you, so again, that's one, so again, it depends on the application, right? If you, and so the question is, yes, you could get into a situation where there is an arrow
because
there.
I think this could be very controversial in fields of IQ and
Right.
ethnicity.
Right. So that's a good question. That arrow would be, But so long as we can draw at least a good long arrow, again, all models are really specified, and if the arrows that you want to draw are not that important, those actually could be very important, then this paradigm, of course, it doesn't work in this way. Okay. Yeah. Thank you.
Thank you.
Other questions? Yep.
Should I go up? That's what you were doing yesterday?
Let's see if you understand me like this. Is it clear?
Well, I'll just come up to you.
Come over here, yes.
I'm taking my cue from Peter.
I kind of wanted to follow up on the question that Richard was asking. So, and you were saying, given that you only need zero mean restrictions, you could actually look at your background information, regress it on the on your native abilities, and just look at the residuals and use those for drawing your long arrows. Is that right?
You could, but you don't actually. So the scholarship, remember, you got to observe it. The native abilities eta and you are never observed.
Okay, that's
the problem. right? Because that's why they're going to the residuals.
Exactly.
Those are the intangibles, right?
Yeah, you're
So
right.
yeah, you can actually screw up the setting in many ways, I think. I mean, yeah, and you know, well, that's yours.
All right,
Does
thanks.
that answer your
That's
question?
an answer, yes.
Okay.
In view of time, I think we need to close this medallion lecture. Let us thank Muli Banerjee again. Thank you very much.
Thank you, Peter. Thank you. Oh, no, don't forget the medal, yes. Okay, my
Yeah, seems to be the case. It is a great pleasure for me to chair the 2024 Ising Lecture, which is organized by the Ruhr University Bochum Department of Mathematics with the intention to commemorate Ernst Ising, who spent most of his childhood and youth here in Bochum. But before giving the floor to Frank den Hollander, who will present the Ising lecture, and before that to Christoph Kulzke, who will say a bit about the Ising model, I want to say some words about the life of Ernst Ising, some biographical data, his relation to Bochum, and the relationship of his family to Bochum. And this is not an easy story, as being Jewish, their lives and hopes and dreams were shattered by the Nazi period. The vita of Ernst Ising, the first part you can read here. He was born on 10th of May 1900 in Cologne. His parents, Gustav und Thekla Ising, were merchants, and they moved in 1904 to Bochum, and where the parents Ising opened a clothing store in the center of town, actually very close to where the train station is nowadays. The same year, Ernst Ising's sister Lotte was born. Ernst Ising went to school here in Bochum, graduated from high school here in 1918, incidentally the same high school that much later my own children attended. And after a short period of military service, he then began to study mathematics, physics, and astronomy, first in Göttingen, then in Bonn, and finally in Hamburg, where exactly 100 years ago, in 1924, he obtained his PhD. In his thesis, Ernst Ising studied a model of ferromagnetism that nowadays bears his name, and which will be explained to us by Christoph Kulzke in his talk. After his PhD, Ising worked for 3 years in the patent office of the company AEG, which was a big electrical company in those days. In 1927, after 3 years of working for the company, he became a high school teacher, first at a private school. Then, after he had obtained the right certificates to become a stage school teacher, he worked at a stage school in Strasbourg, near Berlin. When the Nazis came to power in Germany, on 1st of April 1933, Ising, like virtually all Jewish civil servants in Germany, lost his job. After a brief search for a new position, which also led him as a teacher to Paris, he started working at a private Jewish school in Kapput near Berlin. And the school was actually right next to the summer home of the Albert Einstein family. And because Einstein had already emigrated to the United States by that time, the school actually used the Einstein summer home as extension for the school, which became necessary because more and more Jewish kids came to this school, since it was made for them more and more difficult to attend public schools. After the pogroms had started in 1938, also the Jewish school was closed, and Ising and his wife emigrated to Luxembourg. During the German occupation, Ising was forced to do all kinds of work, mostly forced labor. In September 1944, they were liberated by the Allied forces. Ising survived the Nazi period only because he was married to a non-Jewish wife, which in the completely insane racial ideas of Nazi Germany gave him some protection. After the end of World War II, it took some time, but in 1947, Ising and his wife, together with their son Thomas, who had been born during the period in Luxembourg, could emigrate to the United States. There he was school teacher for a short period, and then he became professor of physics at Bradley College in Peoria, Illinois, where he remained for the rest of his life until he died a day after his 98th birthday in the very same place. I want to show you some traces of the Ising family here in Bochum. I'm not sure how well that is visible. Well, a bit. So what you see here is a map of downtown. You can recognize the ring. Down at the bottom to the right is a central station, so some of the hotels are in that area. And where you see at the top a red arrow, that is actually where the Ising family lived. So they owned a magnificent house. The address was Goethestraße 18, and this is, well, you cannot read that, it's also in German. I'm showing this here to you, first of all, because it gives you a picture of what the street looked like, and it is a picture of the Ising parents, so Gustav and Thekla Ising. So they owned a house, a magnificent house. I will show you in a moment a picture of it, in a part of town where, or in one street it was actually, where Jewish middle-class families built homes in the early 20th century. The cantor of the synagogue, Eric Mandel, is a very well-known collector of synagogue music. He lived next door. On the opposite side of the street was the home of Ottilie Schönewald. She was a member of parliament in Germany in the 1920s and 1930s for the Liberal Party. Actors and musicians from the local theater were frequent guests at the Ising home. I read recently that Ernst Ising actually got some education in how to pronounce things better from a local actor of the Schauspielhaus. And all of this ended when the Nazis came to power in 1933. Life became increasingly difficult for Jewish merchants. There were boycotts. The Nazi government of town advised their employees, strongly advised their employees, not to buy from Jews. Many store owners had to give up and sell their property. The situation became completely unbearable when the pogroms took place on the 9th of November 1938, when all over Germany synagogues were set on fire in one night, Jewish stores and homes attacked. The Ising family decided to leave Germany in 1939. So family, I mean now the parents, Gustav and Ernst Ising, and they could emigrate to Switzerland, where their daughter Lotte had already emigrated to already in 1933. This is an old picture of, so this is what this house looked like. It's not the corner house, but it's the next house then. So I'm not sure whether this is not working. So the corner house on the left is not the house of the Isings, but the next house behind it. And if you go there nowadays, then I took this picture actually a week ago. First of all, the houses have been completely destroyed in the war, and the house number 20 is the gray house. That's the second house that you see there, but well, it's just on the spot where the Isings lives, but it is not their house. What you see here is nowadays a monument that is a part of a list of such monuments in order to commemorate traces of Jewish life in Bochum. And there are, in the meantime, 13 or 14 of those monuments. And so you can read here a bit about it. So on the left it says Jewish citizens that lived here in the Goethestraße. The Jewish residents of the Goethestraße, they were respected citizens of Bochum, middle-class families, pillars of the society, and soon after 1933, they were declared outcasts and the source of all evil. I pass by this location actually pretty much every day on my way to work because I live only 2 blocks away. The location is on the intersection of Goethestraße, which this street is, and the Schillerstraße, 2 streets named after giants of German culture, the poets Goethe and Schiller. And at the same time, you get a glimpse of the abyss of German history. Words cannot express the shame that I feel about what my country did, not 1,000 years ago in the dark Middle Ages, but less than 100 years ago in the middle of the 20th century. I think it is important that this is not forgotten. Now I give the floor to Christoph, and Christoph will tell us a bit about the Ising model. Christoph is a colleague of mine here in Bochum, not only a colleague, but he is an office neighbor and a good friend, so we talk often to each other. And Christoph is an expert on the Ising model and many other things, and he will tell you a bit. Christoph.
Yeah, so the story of the Ising model started with Wilhelm Lenz and Ernst Ising. And Ernst Ising went to the University of Hamburg to get a PhD with Wilhelm Lenz. And the question they were after was how to explain the spontaneous magnetization of a ferromagnet by means of statistical mechanics. What is spontaneous magnetization? If you have a piece of iron and you put it into sufficiently low temperature, so here's temperature, and you put a magnetic field, then it goes into saturation. You can magnetize it. And if you take away the magnetic field, then this value will stay. Now, if you turn on the temperature, the magnetization will go down and has a characteristic shape like this. And this is typical for many materials, and so this is a sign of an ordering of the magnets they have. And the question is, can this be explained by a probabilistic model, namely following the prescription of Boltzmann-Gibbs? Okay, so the idea was to make a model with minimal local degree of freedom. So you take the simplest possible choice of a local state space, how we say today. So the magnetic moments, they can point up or down. And so people knew that metals are composed of atoms which sit on a lattice. So let us take the lattice CD, maybe d equal 2, d equals 3 is the most important choice. And let's take a finite but very large portion, and so we have these little magnetic needles, or random variables, as we say today, which are simply two-valued. And let me say, with a view on what's going to follow, with our main speaker, Frank den Hollander, today it's also interesting to look at other base spaces instead of the lattice, maybe networks, so graphs, and also to give other interpretations of the magnetic moments. For instance, as opinions in a social network. This will be interesting. And then the prescription is look at the configuration, sigma I. So each of these spins, how they are called, can take a value plus or minus 1 in the finite volume, and then write down e to the minus beta times the energy. So there's an energy function, so a real valued function, and this is what you see here, minus the energy. And the main part is this one. This describes the non-independence, so the dependence between these random variables sigma I, sigma j, and this is supposed to mean nearest neighbors on the lattice. And this term is present if we have an external magnetic field, and the sum is over all the I in the volume lambda. So the Z lambda is simply the sum which makes this a a probability measure, so that the sum over all the 2 to the lambda configurations will give you a 1. And so here is the picture, typical picture, many of you will have seen this, taken from the Friedli-Wellenick excellent book, introductory book on statistical mechanics. So here we see a configuration. We have a 2-dimensional lattice. We have a box, a finite part of it. So we have a boundary condition of pluses. In principle, we can take any boundary condition, but this will be maybe the most relevant. And then here we see some configuration with pluses here, with minuses here, and some interfacial lines or contours, which are the border lines between minuses and pluses. And they are very relevant in many studies until today. Okay. And equivalently, you can describe configuration by a set of such contours. And note, if you have a plus here on the outside and you focus on the middle side here, and you're asking yourself for the event that you have a -1 here, you have to have at least one contour, possibly many, surrounding this eye. So this one, for instance, is a very long contour. Okay, so the question is, can we explain this spontaneous magnetization picture that I showed you by this model? So choosing the lambda very, very, very large. And so does this model have a magnetic phase transition? What is actually a phase transition mathematically? Can we make a theory for this? And what is behavior of other quantities? Like, for instance, the magnetic susceptibility, or the specific heat, which is the response of the material. If you put heat to it, it will react in a temperature increase. Okay, so Ernst Ising was the first person in the world who studied the Ising model. And so he finished his PhD thesis in Hamburg by showing that there is actually no phase transition in spatial dimension d = 1 when we have simply a line of these atoms. So he made computations using binomial coefficients and asymptotics of them that were published here in Zeitschrift für Physik in the year 25. And he conjectured, okay, so maybe the short-range interaction is not enough to produce such a phase transition. We need something stronger. And he conjectured, okay, also in dimension d = 2 and 3, this will probably not be the case. So luckily, he was wrong. And Rudolf Peierls, a German-English physicist who also migrated from Germany to England, gave a proof that there is actually a long-range order in space dimensions d = 2 and also d > 2, already pretty early in the year 1936, by means of his famous Peierls argument, which is simply a counting argument and an energetic argument estimating the probability that if you take a very large box and have plus binary conditions, you will find at very large beta at least one contour. So this is very small if the beta becomes large uniformly in the box size. Okay, famous Peierls argument used in many circumstances in different fields, in percolation, in long-range models, etc. So it also gave rise to developments like Pirogov-Sinai theory. So that's the next important step, which was the rigorous solution by Onsager. And so he computed the free energy of the Ising model. So free energy is basically the logarithmic moment generating function of the energy per side, and then the limit. And it's one of the important thermodynamical potentials. So for instance, it can serve to compute, if you have it as a function of beta, the specific heat. And by ingenious combinatorics, a lot of guessing algebra and reducing things to determinants, or rather Pfaffians, he was able to come up with this solution formula for the free energy. And so then it's easy to analyze this formula. and see that there's actually one critical beta where there is a singularity, namely the one where this expression under the logarithm touches 0 for the values where the two cosines are equal to 1, and then you can play with it and analyze it. Okay, and so the critical inverse temperature resulting from this is this one, and you can learn something about the specific heat, for instance. They also managed, together with Kaufmann, to rigorously compute via transformations, algebra, determinants, Pfaffians, the formula for the magnetization, which is here simply the expectation of any spin, let's say the spin at the origin, so this plus minus 1 valued variable, if you put plus boundary condition and choose the lattice extremely large, ideally infinitely large. You'd have to take a limit in here. And what you see is that this curve that I showed you before vanishes as a function of t or as a function of beta minus the critical value as a power law with an exponent 1/8. And this is just an example of a power law. And so if we go a bit forward in time, so measurements with actual materials have shown that in dimension d equals 3, we find for the Ising model a power law like this. So this is supported by experiments, but this is also supported by numerics today and also supported by non-rigorous approximation schemes, which nevertheless seem to work very well. And so more generally, so there's this universality conjecture, namely such models like the Ising model tend to show the same, at least critical behavior, so around the critical point, as, let's say, little perturbations of them. So there are certain universality classes, and they depend only on the spatial dimension, on the spin dimension, and not so much on the microscopic details of the model. So this, let's say, this is a conjecture which has been proved rigorously in not so many cases. And there was, I would like to stress this here a bit, in a strong input, but not a completely rigorous one, from theoretical physics. Namely, there is the physical perspective in terms of renormalization group theory. Renormalization group theory, for which Kenneth Wilson obtained a Nobel Prize in theoretical physics, is the idea to look at, as we would say as probabilists, non-standard limit theorems and look at the system by going back and ignore microscopic details. Now, how this is implemented by block averaging spins or by different means in Fourier space, this is a question. And so Wilson came up actually also with approximation schemes and non-justifiable ideas like continuous dimensions, etc., etc. And so mathematics has not quite been successful to implement or to understand everything that was promised here. But nevertheless, a renormalization group on scaling is of course hugely successful, and so in this sense, renormalization group is a huge success. So from a mathematical point of view, you could ask, what is actually a phase transition? So let's say, what is the first order phase transition? So the one that we see in the Ising model. So there are three people behind the Iron Curtain, and on the other side of the Iron Curtain, the D, L, and R, and they developed a rigorous theory for infinite systems, which we are using today, because only for infinite systems, for actually measures not only on finite boxes, but on infinite, on spaces of infinite configurations, we have good properties, we have shift invariance, we can ask for ergodicity. And so what is this DLR, the Bush-Lanford-Ruel formalism? So it means that the measure mu, we are defining what a state or what a Gibbs measure in the infinite volume is, that should be invariant under a certain resampling in the volume lambda. And the resampling is with respect to these kernels, gamma lambda, also called specification kernels. They depend on the boundary condition. So they are precisely our finite volume Gibbs measures, but with a finite general boundary condition. And if this resampling, so drawing the boundary condition according to mu and then taking expectation with respect to this measure is the same as the measure itself, it's the DLR consistency, and this defines what a Gibbs measure in the infinite volume is. And then this is a fruitful playing ground. Note that the solutions here it's a convex set. Moreover, it's a simplex, so people are interested in properties of the so-called Gibbs simplex in extremal elements, properties of extremal decomposition, etc. And it's also a good play. I mean, it's the appropriate ground to look at large deviations, and I put here the name Varadan. Okay, so another branch, and if you wish, it's a bit in the spirit of the scaling transformation and the renormalization group, but not acting on block averages, but acting on actually curves. So this is stochastic Löwner evolution. So this is a huge success of mathematical statistical mechanics. And it says that in dimension d equal 2, you can describe these contour lines of the Ising model, but also of other models, of the simpler model percolation, certain random walk models, or many other models. At the critical point of the model with a family of random curves, I'm not defining them, so called SLE. Stochastic Löwner evolution, or like some people say, Schramm-Löwner evolution. It depends on the parameter kappa, which captures the model dependence, so it has to be identified. And we have seen very nice talks about this in progress in this area of the two-dimensional systems. And for instance, for the Ising interfaces, which you get, for instance, by taking a boundary condition, which is on the line on the upper half space, and here you put minuses, and here you put pluses, and then you force a line into the upper half plane, this will converge to an SLE3. Okay, so here are the people which have given this to us. First and foremost, Oleg Schramm, and he invented SLE by looking at the old Löwner evolution from complex analysis, which was, I think, very old, like 100 years old now, and had the idea to use Brownian motion as a driving force, and so this generates, via a family of conformal maps, these wiggly curves, and so that was this really brilliant idea. And then was Wendelin Werner and Stanislav Smirnov, who obtained for works on percolation, Ising models, etc., fields methods. Also, Hugo Duménil-Copin, he worked a lot with this, but he also works in higher dimensions and treats the really hard problems in Ising models and similar models in higher dimensions. So let me at the end say something about a variation of Ising models, namely disordered models. So before we were looking, let's say, on a lattice at this beta, sigma I, sigma j, where you sum over the edges of a lattice, and we had an h outside here, and we had a 1 here. Now there's the game motivated from physics or even material science to look at random systems themselves, so with random Hamiltonians, where these coupling constants may not be all equal. Let's say we put them equal to 1. Now they might take two values, let's say 1 and 1 plus epsilon. So that would be a random ferromagnet, or we could also take the HIs to be random. Okay, and particularly relevant is that we have frozen randomness, which means that in the beginning of the game, these coupling constants are chosen from simple distribution and then kept fixed. And then we are asking for these Gibbs probabilities and for the properties of these measures which we obtain in this way. And the idea is that comes, let's say, from physics, from quenching, really freezing a material so that the atoms cannot move anymore, but the magnets stay where they are. Okay, so here's a question that after disorder relevance that we also saw in Rongfeng Sung's talk today in a different context. So in other words, does the randomness matter? And so it's possible that the randomness doesn't matter so much. It's possible that the randomness destroys the phase transition, which is happening, for instance, for HIs symmetrically distributed in low dimensions. It's a well-understood phenomenon. However, it's still with interesting open questions. Or what is the most challenging or most interesting is that there are situations when these random JIJs, in particular where they can take pluses and minuses with the same probability, so one does not know what even the ground states, so the maximizers of the Hamiltonian will be. So then we can expect, or we believe that there are many competing ground states, so maximizing configurations, but they look very strange, so they're not very easy to understand. And so if the beta is very large, then one can probably also in the short-range model create new and highly complex phases, glassy phases. And so there was one contribution from physics, namely by Giorgio Parisi, who obtained precisely for these type of things a Nobel Prize in Physics. Namely, what did he do? He was looking at the mean field spin glass. So he was looking at n sides and looking at the complete graph with n sides and taking the JIJs. It's a famous model, Sheridan-Kirkpatrick model, to be Gaussians with the appropriate variance to have this in a good independent way. And what he was able to do by some computations, he calls himself in his Nobel Prize lecture crazy and illegal. So it's very funny the way how he explains this. So he was able to come up with a formula for the free energy, which is not quite as simple, the famous Parisi formula, as the one that we saw by Ordensager, but nevertheless quite explicit. Okay, and it took some time that Michel Talagrand, using ideas of Guerra, interpolation ideas, was able to actually prove this formula. Michel Talagrand obtained the Abel Prize in this year, and we know him in probability from concentration of measure phenomenon, from method of chaining to control processes which are correlated and control maxima and suprema of these processes. And that was useful in this game. Okay, so nevertheless, we know not so much about short-range spin glasses, so this is still one of the open problems. And so more broadly speaking, we could also now not just take the lattice and have random interactions, but we could look at spatial or geometrical disorder for the graph on which this spin system sits. And so the first thing would be, if we are coming, let's say, from physics, to look at dilute lattices. But we can also look at random networks, for instance. And so maybe with a different view, do the interpretation of the Ising model. Or we can now look at other two-state models which interact. And so, for instance, today, people are looking at networks, also networks which are maybe generated by point clouds or by point processes in Euclidean space. Then there's a point where I didn't say anything, namely that of the spin dynamics. So there's a natural stochastic dynamics, which has these Gibbs measures as invariant measures, and it's very interesting, especially in infinite volume, to study that. And but you can do this on networks, for instance, and look at the opinion dynamics on networks. And so there are two specialists in this field, which is Remke and Frank den Hollander, and I'm extremely happy that we will talk about this now. And he makes even things like he looks at dynamical networks and look at the co-evolution of this type of models. And so thanks for your attention.
Thank you very much, Professor. And so now we come to the Ising lecture, and it's a great pleasure for me to introduce Frank den Hollander. I've known Frank for a long time, basically from the moment on when I came to the Netherlands in 1988. Frank obtained his PhD in physics from Leiden University. He then was a postdoc at Delft, spent some time on his first tenured position in Utrecht, and then moved on to become full professor at the University of Nijmegen, moving from there to Eindhoven, where he was director of the Stochastics Institute Urandum, and then in the final move from Eindhoven to Leiden, where he is now a professor of mathematics. Frank's research spans quite a broad variety of topics. So I just name a number of things. Large deviations, he wrote a book on large deviations. Metastability, there's also a book by Frank on that topic. Random networks, interacting particle systems are some of the keywords. Frank has received all kinds of honors that you can receive. He is a member of the Royal Netherlands Academy of Sciences. He has received an ERC advanced grant. He has received major funding from the Dutch government for his work on networks. He was a plenary speaker at major conferences, invited speaker at the International Congress of Mathematicians, European Congress of Mathematicians. Okay, I could continue like that, but now I will give the floor to Frank. We are very, very grateful that you accepted our invitation to present the Ising lecture. Frank.
So thank you, Harold, for your very kind words. It's indeed a pleasure and an honor to be here and deliver the Ising lecture. As Christoph Koolske already explained, Ernst Ising stood at the beginning of 100 years of very successful developments in mathematical statistical physics, the area where physics and mathematics come together to study cooperative phenomena and in cooperative behavior in large interacting stochastic systems, and with such famous things as phase transitions and criticality. And this is what Christoph explained. Now, the topic of this lecture, evolution of discordance, and I will have to explain what that means, is very much in that tradition. We're going to talk about large networks, we're going to talk about flows of opinion on that networks, and we're going to be zooming in on the spots in the network where there is disagreement between the different opinions, and we're going to try and see what is going on there. So the setting in which we will be working is that of a friendship network. So here's a snapshot of a friendship network, and you should imagine that individuals are represented by vertices, and their friendships, and friendships are always mutual, are represented by edges, and these individuals talk to each other, and because they talk to each other, they may change their opinion. And we're going to try and see whether we can model that. And as Christoph already said, we're going to do this really in a kind of random graph context, large random graphs, large because friendship networks are large, and random graphs because they are typically very complex and very large. Okay, so here are some key questions that you face when you see such a situation. You're going to say, okay, opinions can change, people can try to convince each other, so how are these opinions going to evolve through your network, through your friendship network? And in what way does the architecture of the network actually influence that? It's clear that the network determines how these opinions can flow, but what is crucial and what is not so crucial about the network for understanding how that happens? And imagine what would happen if the network is, while these opinions are moving around, itself is changing. So it could be that edges, so friendships or edges could be added or removed. People become friends, people lose friendships. So what sort of effect could that have on the flow of opinions? And even a more difficult question, which we refer to as coevolution, what happens when not only do the opinions flow in a way that depends on the network, but the updating of the network also depends on the opinions that are on the network. And in particular, there will be a keyword, polarization, that I will come to towards the end of the lecture. And the answers to these questions are mathematically very challenging. Great, let's go and see what we can say about it. And in fact, in what follows, I will give you a brief overview of what we know and what we do not know concerning these questions. And the area is very rapidly developing, and interesting things have been done, and I will be able to tell you about that, but there's also a lot that we still do not know, and that remain really hard questions for us to deal with. So, in this lecture, we're going to focus on random opinion dynamics on a random graph, a graph G with a vertex set V and an edge set E. And we're going to be looking at various classes of random graphs. There we will be encountering sparse graphs, where the number of edges is comparable to the number of vertices, which amounts to saying that the degrees of the vertices are of order 1, are finite numbers. But we're also going to look at dense graphs, where the number of edges is proportional to the square of the vertices, which means that many vertices are connected to each other. And those are two very distinct cases that will show up in what I'm going to tell you about. And we will be particularly interested in looking at the discordant edges. So those are the edges linking vertices that have different opinions, because it is on those spots that the action is going on, where people can change their opinion. And we will be encountering different timescales on which this flow of opinions occurs, and we will be able to write down in a number of cases even some evolution equations for key quantities describing these densities or fractions of discordant edges or fractions of opinions. So a typical picture would be something like this. You have a random graph, and you would see at some point that there's a group of vertices that have a red opinion and a group of vertices that have a blue opinion, and it is the boundary between these sets where people or vertices may start to change their opinion, and that boundary is moving. And that is what we're going to focus on for several choices of random graphs. And to make life simple, we're going to be talking about two possible opinions. There are models where you can have 3 or more different opinions, but let's talk about 2. So it's an Ising model for 2 opinions on not a lattice, but on a random graph. Now, we're also going to distinguish between two types of dynamics. I will spend a part of the talk on a situation when there's a one-way feedback. This means that the graph is there, either static and it doesn't do anything, or it moves, but it's doing that completely autonomously, and then the opinions live on top of that autonomous object and start to change. So that is a one-way feedback, because the opinions do not influence what the graph is doing. And then we're going to, in the second part, going to move to a situation that is a two-way feedback, where both dynamics mutually influence each other. And it will turn out that in the first case, mostly what you see is opinions moving, and if you wait long enough, there's going to be consensus. But in the second case of the dynamics, there's an interesting phenomenon going on, which is polarization. Polarization means that communities split in two, and they don't want to talk to each other anymore. They are convinced of their own opinions. Look at what's happening in the US and the elections there. And this is a very mathematically tricky problem, and we're going to try and capture a little bit of that, but much of that is still going to be in the future. So, let's first look at one-way feedback models. So I'm going to look at a graph and run what is called the Voter model on this graph. The Voter model was introduced by Holly and Liggett in the mid-70s. So we are given a finite connected graph G, and the Voter model is, on this graph, is a Markov process that has a configuration space where at every vertex you either have opinion heart or opinion spade or diamond, sorry. And I took these symbols, rather than 0 and 1, let's enjoy ourselves a little bit. And what happens is that every vertex has a clock, and at rate 1, when that clock rings, what the vertex does, it says, let me randomly pick a neighbor, and let me adopt the opinion of that neighbor. So it amounts like, when the clock rings, I go and talk to one of my friends, and whatever the opinion of that friend is, he convinces me to take that opinion. Maybe he already had the same opinion as I had, then I won't change opinion, but if he has a different opinion, I change my mind. Now, this is a particular way of talking about how opinions can change. There are many other choices you can make, but we're going to focus on this model, and it's called the Voter model. So the Voter model proceeds by randomly selecting a neighbor and then adopting the opinion of that neighbor. And at any moment of time, there is a configuration, XCT, and XCT consists of a number of variables, heart and diamond, and that whole configuration evolves over time, and that is what we are going to talk about. And we're going to be interested in the discordant edges. So discordant edges at time t are those edges whose opinions at their ends differ. And differ is enough because we only have two possibilities, and so differ means one is heart and the other is diamond. And we're going to be interested in the fraction of discordant edges, where you divide by the total number of edges, and you say, okay, what fraction of my edges is currently discordant, and that will evolve over time because the configuration of the Voter model is evolving over time because of the mechanism of changing and adopting opinions, as I said. So that's the model that we're looking at, and here you see a picture where in the background there is a graph. For the moment, this graph is going to be fixed. Later, we will make it dynamic as well, but for a while, it's going to be fixed. And every vertex at a certain moment has an opinion, and the way these opinions evolves is via this random selection and adoption mechanism. Every vertex looks after an exponential clock rings at rate 1 at a neighbor and adopts the opinion. So the graph stays fixed here, and you see these opinions evolving over time. And that's what we're going to try and describe. Now, the consensus time is the first time at which we see that all the vertices reach the same opinion. And there are two ways they can do that. They can either all be heart or all be diamond. And when that happens, the model sort of stops, because there are no different opinions anymore, and when people keep on randomly selecting the neighbors, nothing is going to change anymore. So this is the status quo where everybody has the same opinion, and if your graph is finite, you know for sure that sooner or later you're going to reach one of these two states. That's no mystery. But the interesting question to ask here is, how long does it take before this happens? So what is the relevant time scale on which you see opinions really changing? And can we describe how we will reach these consensus states? So the question will be, you are given a large friendship networks and you have this opinion change, and you say, okay, how long do I have to wait until I see that everybody sort of gets the same opinion? Is this 10 days or is it 100 years? And what happens along the way towards this consensus? Now, what I'm going to do next is to look at a number of examples of graphs and then try to describe what this opinion dynamics, this voter model on that graph is doing, and the answer will very much depend on the choice of the graph that we make. Clearly, if a graph has many edges, things should be going faster than if it has few edges. And we're going to try not only to describe this qualitatively, but also quantitatively. Let's see if we can really compute things and get an answer, and determine relevant timescales, and let's see how this consensus is being reached. Okay, so let's try and do that for a number of graphs. And what do we know nowadays, and what can we say about this question? As a prelude to anything, you should start with the most simple graph that you can imagine, and that's the complete graph. So that's the graph where you have n vertices and every pair of vertices is connected to each other. This is what we call the mean field setting. And for the mean field setting, you can by hand compute everything that you want to know. And let's do that short computation and see what is happening, because this should be revealing for what is going to happen for other types of graphs. Now, we're going to monitor the number of opinions of heart, which we write with a straight OT, and the n upstairs is to remind you that this is a complete graph with n vertices. And it is very simple to see that this number performs a continuous time random walk. Life is really very simple here. On the set 0 and n, up to n, and 0 and n are traps, because they correspond to everybody being diamond or everybody being heart. And you can easily see that the rates at which this nearest neighbor random walk goes up and down are given by the numbers that I've written here. And they are the same, to go up and to go down, so it's a symmetric random walk. So this is really a very simple problem. And what you do is to scale. You say the total number of vertices is n. Let's divide the number of vertices of type heart by n. And let's take n going to infinity. What do we get? And it turns out that this fraction of opinions heart moves on scale n, so you have to scale up time by n, otherwise you see nothing happening. And it converges to a very simple limiting stochastic process, which most of us have encountered, and it's called the Fisher-Wright diffusion, and it's written here what the Fisher-Wright diffusion is. It's a stochastic differential equation. It's a diffusion driven by a standard Brownian motion with some sort of specific diffusion function in front. And here is a picture of a realization of the Fisher-Wright diffusion. You see that this Fisher-Wright diffusion gets trapped when it hits 0 or 1, which corresponds to this full consensus. And it is performing some sort of motion until it does that. And this Fisher-Wright diffusion is a very well-known object. And in fact, if you've ever taught a course on the Moran model in population genetics, it's the same computation. The photo model on the complete graph is the same as the Moran model in population genetics, where opinions become genetic traits, and choosing a neighbor on the complete graph means choosing randomly a neighbor which corresponds to what we call resampling. So this is a known and familiar object for us. And the number of discordant edges can be immediately expressed in terms of the number of opinions of the two types, obviously. And so, if you go to fractions, the fraction of discordant edges is a deterministic function of the fractions of the two opinions. And apart from a trivial factor n over n minus 1, it's just the product of the two fractions. You'd say, well, sure. I mean, you have a mean field situation, so the fraction of discordant edges should be the product. Yes, on the complete graph. And so as a consequence of this earlier convergence of the fraction of one opinion to the Fisher-Wright diffusion, you get that on the same time scale n, your fraction of discordant edges is going to converge to a process that is just the Fisher-Wright diffusion times 1 minus the Fisher-Wright diffusion. So in this very nice mean field setup where everything is simple, the computation can be done completely, and it looks nice, and it gives us a hint of what we might expect. And now let's go to random graphs. None of this works on random graphs. For one thing, the fraction of a particular type is no longer a Markov process, because you need to know the structure of the graph. And so this falls out of the window once you go to a random graph. Let's see what we could do. And we hope that if the graph is large and in some sense sort of homogeneous, that something like this factorization ought to be popping out in some sort of form, but let's see whether we can do that and what it gives. Now, the first random graph that I'm going to look at is the random regular graph. It's a little step upward where you say, I have a graph of a fixed degree. So a random regular graph of degree d is you look at all possible graphs of n vertices where all the vertices have degree 3, and you randomly choose one of them, and that is the outcome of your random regular graph. And there's a very simple algorithm in which you can generate such a graph, which has to do with the configuration model, but let me move on and say, okay, so this is the graph that we're going to look at. It has n vertices, it has dn over 2 edges, which we're going to abbreviate by m, and here you see a little picture of what such a graph would look like. Now, what can we do for this random graph? Okay, there was work by Chen, Choi, and Cox in which they showed that the fraction of one opinion, let's say the heart, on the time scale n, also on this graph, converges to a random process. And this random process is again a Fisher-Wright diffusion, but in the Fisher-Wright diffusion appears a certain diffusion constant that depends on d, and that is no longer 1. It was 1 in the complete graph. And this number is d minus 2 over d minus 1, where d is the degree of your random regular graph. And the proof of this requires martingale techniques and various approximation estimates, and it is in fact a version of what started earlier in the 1990s, which we nowadays talk about as the Cox-Graven finite system scheme, in which they looked at infinite particle, interacting particle systems and blocks of interacting particle systems, and wanted to ask themselves the question, well, how does the behavior on a large block compare with what the behavior is in the infinite lattice? And what we're doing here is a bit of the same. We're having a finite graph, and we're going to run this dynamics, and we're going to have to see some sort of behavior or crossover between short times and large times, and we will see that in a second. So when it comes to the Fisher-Wright diffusion, there's a general work by Chen, Choi, and Cox, and they have a general expression. If you work this out in this particular setting, you see that there is an interesting diffusion constant coming up that is equal to d minus 2 over d minus 1. And the reason why this can be done is a very important reason. The Voter model has a very beautiful dual, coalescing random walks. A dual is another particle system that has that is in some sort of one-to-one relationship with your original model, and this is a very powerful tool, and since we know how to compute with random walks, we can do a lot for the Voter model because of this well-known duality. So here is an important result that comes from, that describes what is happening on the deregular random graph. And it talks about how the average fraction of discordant edges is evolving over time. And what you should immediately see from this formula is that there are 3 time regimes. There's a short time regime, there's a moderate time regime, and there's a large time regime. And why is that? Let's look at what we let this expected value of the fraction of discordant edges be. And t of sub n is any time that you may choose. So it's completely flexible as a function of n, but n is going to go to infinity. And as long as Tn is much smaller than n, this is what I would call the short time scale, this exponential factor is 1. It doesn't change. Now, there is a function in front, which also depends on Tn, and this has an interesting interpretation. It's the probability that when you start 2 random walks on an infinite deregular tree, and you ask, what is the probability that you do not meet up until time t, then that's the function f dt. And this function is clearly going from 1 for t small to a limit, and this limit actually turns out to be d minus 2 over d minus 1. And so you see there's a short time at which this exponential factor isn't doing anything, and then there is a certain profile. I'll show you pictures in a second. Then, by the time Tn becomes of order n, this exponential starts to change. So that's the moderate time regime. And when Tn becomes very large compared to n, you're in the very large regime. This exponential is 0, and it tells you that your expected fraction of discordant edges has reached 0. So, so this function has a nice shape. It goes from 1 down to the same number theta d. And as I've just explained, this corresponds to short time scales, moderate time scales, and long time scales. So on short time scales, the Voter model says, it looks as if I'm living on an infinite regular tree. I don't notice that the graph is finite. But after a while, it starts to say, hey, I'm not on an infinite tree, I'm on a finite graph. And the behavior starts to change. And then after a very long time, it has sort of gone all over the graph. And it says, okay, I'm about ready to get consensus. So this is an important message that comes from this underlying graph structure. Here are some simulations. The upper picture is the short time regime, from 0 to 5 times the number of vertices, which in this simulation is 1,000. And then on a longer time scale, you see that the fraction of the blue curve is what is described by the Fisher-White diffusion, the fraction of hard opinion, and the other one is the other opinion. So you see that there's a diffusive behavior as we have found, and eventually you reach consensus after a random time. Okay, so far so good. That was a first step towards a graph that is random, and we see some interesting phenomena happening. There's again a Fisher-White diffusion appearing, but there are interesting parameters and functions that come into play. The next thing that you would like to do is say, well, let's look at graphs with different degrees. So why not have half of degrees 5 and half of degrees 7, or maybe some other choice? And for those of you who know the configuration model, there's a way to do that. Can you do the same thing for such a graph? No, we can't. It's too difficult for the time being. We're not giving up. And we do not even have a guess of what we should expect. We expect the same type of theorem, but we do not even have a guess of what these quantities fd, t, and theta d could possibly be. No idea, and that's where it is for the moment. You could then say, well, why don't we go to directed graphs? Directed graphs are graphs where arrows friendship have a direction, so there's an in and an out. So, oh gosh, that's going to be even worse. Remarkably, no. It turns out that when you make the graph directed, you can again do certain things that you cannot do for an undirected graph. Surprise, surprise, I did not expect this. And here are two works that do that, and they have, with various elaborate techniques and coupling and comparison, have been able to prove that the same theorem holds, and they have been able to find an expression for what this diffusion constant in the Fisher-White diffusion will become. And it will start to depend on how you choose all your in degrees and your out degrees. So for every vertex you have to determine how many, what are the number of out degrees and in degrees. You have specified that, and then you randomly draw a graph with those in and out degrees. And for instance, if these two in and out degree sequences are the same, we call this the Eulerian graph version, then they are able to write down a formula for what this diffusion constant is, and it looks different from what we had before, and it looks nice. And we do not have any version of a result like this for the undirected case unless the degrees are all the same. Remarkable that we are not able to do that. Before I go to the two-way feedback situation, let's see what happens if we would add some dynamics to my graph. So let's go back to the random regular graph, where every vertex has degree d, and let's run the Voto model on this graph, but let's now also add some dynamics to the graph itself. And what we're going to do is a rewiring dynamics. We're going to say every pair of edges has a clock, and when this clock, well, this clock rings at rate nu divided by twice the number of edges, and nu is a parameter, and when that clock rings, the edges break up and they cross the connection. And so this is what we call random rewiring dynamics, and there's a parameter involved, and this parameter is chosen such that as the network gets very large, any given edge is involved in a rewiring at rate nu. So this nu is now a volatility parameter for the dynamics. And we're going to ask, let's run the Voto model on this random regular graph degree d with this kind of rewiring, and let's see what happens. The rest of the model is the same. And in work in progress, we find that for this case, we can again prove that the same theorem with the three regimes, short, moderate, and large, are true. All the things are the same, but the diffusion constant in the Fisher-Wright diffusion changes. It becomes something different. And what it becomes is written here. It's 1 minus a certain number divided by a parameter beta d, which is square root of d minus 1. And this number is a continued fraction. Wow. I mean, it's not something like d minus 2 over d minus 1. It's an infinite continued fraction. And the way this is written here is what is called in the Pringsheim notation. So it's 1 over 2 plus nu divided by rho d minus something, and then it repeats itself. And it's an inhomogeneous continued fraction. So, big surprise that we could derive this, and it comes from all sorts of coupling techniques and recursion arguments. And your reaction could be, wow, isn't that terrible? No, continued fractions are your friends. They're beautiful objects, and they're lovely. And we can really use this object to sort of see how does this depend on d, how does it depend on nu, and there are interesting properties happening. And for instance, you can show that as nu gets bigger, this diffusion constant increases. So it's strictly increasing in the rate of the dynamics. So what is this telling you? It's saying as your edges rewire faster and faster, you're going to diffuse faster and you're going to quicker reach consensus. No, reasonable, but not obvious. Go and prove it. And this formula proves it. Right? So there are many things that you say, well, more noise should make things happen quicker, but that's not obvious. And here it is. We have been able to really quantify this in detail. Good. Now a bit about two-way feedback. I'm having another 10 minutes to go, and I want to tell you about what we can do when we are looking at a random graph, dynamics, and the Voto model on top of this graph, and the two influence each other. And what I just talked about was a dynamic graph, and it just went autonomously on its own, and then on top of that, the Voto model was trying to move, but the Voto model did not influence the dynamics of the graph. And now we want to describe what happens when such a two-way dynamics happens. Now, this area is difficult, because this is what we call coevolution. Two dynamics that evolve together and that influence each other. So there are many open questions here. there were a few papers suggesting for particular kinds of dynamics certain, based on simulations and heuristics, what might be happening. And one of the things that they found out, but only heuristically, is that for these models with feedback dynamics, you start to have the option of polarization. That is somehow that the vertices split in two communities that do not want to change anymore. For instance, you could say, when you are a discordant edge, you can only disappear, and you can never switch on a discordant edge. Well, that's an extreme dynamics, but after a while you see that discordant people no longer talk to each other, and I have split in two communities that do talk to each other, but they all agree, and between the two communities there's no interaction going on. And there were a few of the conjectures that were raised in the earlier papers were settled by Basu and Sly a couple of years ago, but much remains to be done. And I want to talk about one particular model where this coevolution, this two-way feedback is going on, and see what we can get, and whether a situation like polarization, where there's a big rift between two communities who do not interact with each other anymore and they will never change their opinion, whether we can capture that. And that is the challenge that we're doing. And so what I'm describing is work in progress with Adrien Rayan and Siva Traya. And what we do is we take n vertices, we do two things. The edges are updating their opinion just as they did before, like in the Voto model. They look at neighboring vertices when they have them and adopt their opinion, and this happens at the rate eta. This is one of the parameters. But we also let the edges change their status. So edges can become present or absent. We can call them edges or non-edges. And when an edge is present, it will stay present or become non-present at a rate that depends on what the two opinions are at the end, in particular whether these two opinions are concordant or discordant. And also, when an edge is not present, it can stay not present, or it can become an edge at rates that depend on whether the vertices at the ends are concordant and discordant. And this you can all capture in 4 parameters that describe the probability that you make the switch depending on what your opinions are at the two ends. And there's a total rate rho for every edge to start to consider changing its status. And again, we're going to be interested in what happens when n gets very large, and is there some kind of limiting behavior of the density of opinions and the density of discordant edges. And indeed, what we're trying to do, and making good progress, but we're not there yet, is let's start by initially making all the edges and vertices ID opinions and ID presence or non-presence. And let's follow what the fractions are doing over time. And what we are obtaining is a set of 2 coupled equations, one for the density of the connected vertices and one for the density of opinion heart. And you say they're coupled because the lower one is again some kind of Fisher-Wright diffusion, but there is a diffusion constant that depends on the solution of the first line. And the first line is not a stochastic differential equation, it's not a diffusion, it's a stochastic flow. It's a drift term in which the Qt, which is the solution of a stochastic differential equation, enters. So these are coupled equations, and the drift is written there. Now I'm about to round off. I'm going to show you 2 slides of simulations of what happens when you run these 2 equations, or even better, we run a full simulation and see that it fits with these 2 equations. But before I do that, let me remind you that okay, so there's a lot of mathematics behind this, which I'm not talking about at all. In order to prove what I just said, you need to use graphon theory, dense limits. There are special path topologies, coupling, and all sorts of things. This is what makes us very happy, but that's what you need to do. And here are 2 slides with simulations. We took choices of these parameters, a network of size 1000, and you see simulations of what the fraction of the 2 opinions are. And now the pictures are not for diamond and heart, but for 0 and 1. And so you see there is something Fisher-Rye diffusion-like. And if you look at what the density of the edges are doing, you can look at fractions of concordant edges and discordant edges, or concordant non-edges and discordant non-edges, and they are given by these green and red curves. And you see before these curves hit 0, there is a kind of stochastic flow, and by the time they hit 0, it becomes a deterministic flow. And there are certain choices of these parameters. For instance, you forbid discordant edges to come on to go from a non-edge to an edge, where you would see that there is polarization, where these 2 communities simply wobble around for a while, and then there is no contact anymore between them, and they have separated. And this is the phenomenon of polarization that we can capture here and that we can also quantify here. So I'm done, and give you a take-home message. Co-evolution of opinion dynamics on dynamic networks poses a lot of mathematical challenges. I've been able to show you a few things that we have been able to do over the years, but much remains to be done. And I think I'm on the safe side when I say this problem will remain at the forefront of network science for years to come, and that is great fun. Thank you.
Thank you very much for your very, very nice lecture. So, are there questions?
Frank, brilliant talk. Thank you very much.
Thank you, Gesine.
It's amazing what's known. It's amazing what's not known. So you say the configuration model is hard, but can you say something in the Chung-Lu model, which is sort of the probabilistic version of the configuration model, where you know the weights, you just have edge probabilities, a bit like in homogeneous?
No, because the Chung-Lu model is a kind of special case where you say the degree. So it becomes an inhomogeneous model where you have a product measure. We cannot even do that. I'm full of hope that at some point we will be able to do that, but the current techniques need a lot of change. And it was sort of a miracle that when you go to directed graphs, the directedness is not fighting you, it's helping you. I never expected that. And when these papers came out, I was mesmerized by them. But there are lots of graphs for which we still have to do this.
Thanks.
Further questions?
Thank you. What role does the influencers play in consensus time or in polarization? I think you explained. Could you say more about this?
So there is a consensus time and a polarization time, and you say what influences?
What role does the influencers play in this? I think
I would need to put them into the model because the influences are not there. That's, of course, a very relevant question. If you start to talk about social networks, people are not just only talking to each other, they look at media and they're being influenced. So that's a very interesting question. You would then say there are some other people who are changing the dynamics, and that's a very relevant question. There's no mathematics there. I mean, in this area you have lots of suggestions what might happen, and sometimes you may guess, but try and quantify it, try and compute the quantities. That's very hard. So there's no mathematics for this problem yet. Okay.
Yes. Frank, it's a simple question from someone who doesn't know much about this model. I know there's an anti-voter model, but you chose a voter model. Is there a reason, or is it because that is already subsumed in the work here?
I chose the voter model because I want to describe opinion dynamics. And the voter model is extremely nice because it has a nice dual. The dual is coalescing random walks, and that's a wonderful tool. You can look at other processes on random graphs, contact process, stochastic easing model, so a dynamic version of the easing model that Christoph talked about. They're all wonderful questions, but often they're also very difficult. So there's a whole area of interacting particle systems on random graphs that is fantastic to talk about. The voter model is among the easier ones. And you can make more progress, and you see that even when you add dynamics.
But it's not subsumed. It's not subsumed in your work.
Yeah, it's because the voter model has this nice dual, and you use the dual to really get all these results. If you would not have this dual, it would be so much harder to get your hands on this thing.
Okay.
Yeah. Yeah.
The work leading to polarization is very interesting, but it begs the question, can one do something about it, right? I mean,